Okay, we are recording, and now I'll go back to this share. Current slide. So anyway, the last time we looked at the Montrose contingent valuation study, which was based on action to get rid of an existing problem, in this case, a large amount of DDT, along with pesticide that was released off the coast of Los Angeles by the world's largest DDT plant. And the other approach, and the approach that was used in the Exxon contingent valuation survey that I was involved in, and also more recently in the contingent valuation survey for the British Petroleum Deepwater Horizon spill in the Gulf of Mexico. And anyway, if you want to look at the BP spill, the paper on that, including all the materials, are in a 2017 paper in Science. So in this case, we're going to conduct the study for the state of Alaska and the US government. And one of the things that comes into play in these studies is that they're government trustees for various natural resources. And so in the US case, states, which would be provinces in some places, are trustees, and they're then government agencies. And so in here, NOAA, the National Oceanic and Atmospheric Administration, is in charge of marine mammals and coastlines and things like that. And the US Department of Interior is in charge of birds and other wildlife and national parks and wilderness areas. So anyway, so what you can think of here is we've got two trustee agents, one that's sort of the trustee for all the sea things, and one that's the trustee for the land-based claims, including the wildlife that lives there. And this was the first big use of contingent valuation for this purpose, and it was motivated in large part because there was a major court decision, a major federal court of appeals decision entitled Ohio versus US Department of Interior. And the court in this case ruled that the public needed to be compensated for a term that they made up called passive use value, which they defined to be existence value plus option values. And anyway, the term stuck. Economists typically are more comfortable with non-use value, but they all mean the same thing. And so they said, yes, if you're compensating the public for an accident that harmed resources that the government is the trustee for, then you should count these passive non-use values. And that was necessary to make the whole public whole. That means compensate them so that after the compensation, they suffer no loss. And the caveat there was that contingent valuation was appropriate for doing this if it were reliable. And the court didn't quite make a judgment on that. It sort of made a case that it was until somebody had shown that it wasn't. And so this is going to be an in-person survey of a little over 1,000 respondents. And again, this is going to be administered nationally by this big survey firm, Westat, who does lots of the big US government surveys, including those for the Center for Disease Control. So the survey is going to open. Respondents are going to be told that the general purpose of the survey is to elicit the public's views on different policy issues. At the very beginning, we're going to run through a set of questions, and this is pretty common to these surveys, to get them before you get into the actual subject of this, to recognize that there are lots of competing programs. The government's doing lots of things. So we administer a standard battery of questions on that. And then they're told explicitly that the main focus of this survey is going to be on a proposal to prevent another spill similar to the Exxon Valdez. So we're going to start by showing respondents where this Exxon Valdez spill took place. And so we point, the first thing the interviewers do is that they have this big picture book that they sit in front of people. And in the upper right-hand corner, they're going to show people the state of Alaska, which doesn't touch the actual US, it's above Canada. Because the US bought this property from Russia long ago. And anyway, the state of Alaska is huge, and so it's very remote. And then we're going to tell people that the reason this happened is that the oil in Alaska is located way up on the Arctic Circle at a place called Prudhoe Bay. It goes down a pipeline to this small town called Valdez, and then it gets loaded onto tankers. So we're then going to show people this is a pipeline, this is where it goes into Valdez, and then these are the tanker routes. So the tankers come in and go out, and the Exxon Valdez shipwreck is going to occur because the ship hit this reef here called Bly Reef. And so what the interviewer is doing while this book is in front of people, this large binder, is point all these things out. Okay, so again, there are words that go with this, but I'm going to tell it mainly in pictures because that's what people tend to take away from it. So we're going to show people the setting where it took place. And so Alaska is really far north, and it's both cold and dark most of the years. And so down here in the bottom left is the Port of Valdez, and then this is the narrow sort of straits where the tankers go out. So this is where they load the tankers and they go out. We then tell people that the sort of proximate cause for the spill was that the tanker moved out of the shipping channel to avoid a glacier, an iceberg that was in the shipping channel. And we show them what that looks like. Then we're going to move into describing the wildlife that were harmed. So they're going to get shown photos of the different types of wildlife. I'm not going to show you all of those, but there are several species of birds, and we show them pictures of the main ones. And they're marine mammals, sea otters, and whales in particular that are harmed. We're going to provide estimates on the number of different types of animals that are killed, the population sizes in Alaska to put the number killed in perspective, and the time for the population to recover. So all of this information is coming from the scientists. And that's a key thing to think about as we go through these surveys. The scientists have to provide, this is something that the economists don't do by themselves. They provide all of this. And there's a huge amount of work that sort of goes into coming up with all of this. At one point, there are these birds called murres that look like miniature penguins, and hopefully they show up reasonably well on your screen. Hundreds of thousands of these murres were killed. And it turns out it's really hard to estimate how many were killed because foxes and other animals eat them as they wash up on the shoreline. And so they actually dropped, tagged murres out of airplanes to see how many would be recaptured in different ways. So behind the scenes, there's a huge amount of science work going on in this study, and I'll point that out as we go along. Okay, so we killed about 5,000 sea otters. In these surveys, this is a case where we went to a huge amount of effort to find pictures of sea otters that were accurate, that didn't have oil, where the sea otters were not overly cute. Okay, so anyway, there are a whole bunch of these pictures we show other types of birds and other things, and they're also being shown cards that have these population numbers. So now we're going to describe the path and extent of the shoreline oiling. So here we're going to show them X marks the spot. This is where the tanker ran aground on the shore, on the reef. And then this is the path of the oil. So for this path of the oil, there has to be, an oil dispersion model, and then there has to be ground truthing on all of these islands, pointing out how much oil there is. So we distinguish between heavy impacts and moderate to light impacts here as we go along. And then one of the things that happens, this isn't a phenomenon the physical oceanographers who model this know very well. If the spill is really close to shore, the oil will tend to come ashore in a really narrow spot. And for instance, there was a sister ship called the Amico Cadiz to the Exxon Valdez that had a big oil spill in France, and almost all the oil came ashore in a very small area. But if you get the ship just far enough out, the oil will then wrap the coastline for a long time. So here we basically, and there are actually a couple of these, we showed them that the oil is continuing to wrap the coastline. In this case, actually wraps about 1,000 miles of coastline. And that's in part why this was considered such a disaster. And what happens is that the birds, in some sense, see the oil, and the oil looks like food, and so the birds are attracted to the oil. And so the thickness of the oil actually gets, at some level, it gets more deadly as it thins out. So we show the people what very heavy oiled shoreline look like. We show people what different degrees of oiling look like. This is a heavily oiled shoreline. We also show people, because our research, our focus groups and things here, one of the things people were sort of really concerned about was, did Exxon and other people try to clean up the oil? And so we go to a lot of effort to show people that because remember, what we're going to be doing is we're going to be selling people a plan to prevent a spill so that this doesn't have to happen. But anyway, people wanted to know what the cleanup effort looked like. And this is a case where the cleanup effort tended to do more harm than good. And that was something they learned because NOAA engaged in active experimentation. They took some of the beaches and they didn't clean some of these rocky shorelines and didn't clean them up. And what they found was that these high pressure hot water hoses tended to kill the bacteria, which broke down the oil. And so the unclean beaches actually recovered quicker. So now we're going to tell people about a plan to prevent a similar future spill. So respondents are going to be told that there's a risk assessment that shows on average there's going to be about one very large spill similar to the Exxon Valdez every 10 years. And this matches both the actual experience in shipping oil on the route and the original risk assessment that was done before they started shipping out oil. And this is a classic case where the people who did the original analysis got everything right. And the oil companies argued over the years, since no spill had happened, that they could cut back on what they were doing to prevent spills. And in some ways, we put back into place a version of the original sort of plan. And we'll see that here. So we're going to have a spill prevention plan. It's going to have a set of measures ranging from import checks. There were all this concern that the captain was drunk, which technically didn't matter because the third mate who had a pilot's license was sailing the ship, to being able to monitor the path of, oh, this is tank. That needs to be here. Tank is not good. Okay, from current slide. Okay, to being able to monitor the path of the tanker, they had a radar system that was capable of looking down the channel, and they pulled it out at one time because it was expensive to operate. But the centerpiece of this plan is going to be that the tanker is going to be accompanied until it gets out to the sort of ocean part of the Prince William Sound by two ocean-going tugs. Those ocean-going tugs are going to be able to keep the tankers from hitting reefs, and then they're going to be able to deploy booms quickly if oil is spilled, and that's actually the key to preventing the harm from oil spills. So here's what the plan looked like, and again, what really makes these surveys different from conventional surveys is you're selling people, a real life plan. And so there's an escort ship. The escort ship is going to be able to deploy these booms. We actually called these things Norwegian sea fences out of some industry magazines that were selling these things. There was a Norwegian company, and anyway, they started manufacturing them that looked just like ours, and anyway, they became popular to actually deploy. So that's an odd notion. So anyway, here's the tanker. The Exxon Valdez, two compartments had been punctured when it ran into the reef, and so anyway, here's the escort ship, one of the escort ships deploying its boom to quickly contain the spill. So what does the willingness to pay question look like? It says that present government officials estimate that the program would cost your household a total of X, where X is going to be a randomly assigned cost amount. You would pay this as a special one-time charge on your federal income tax. The money would only be used for this purpose, which is preventing another large oil spill in Prince William Sound. And then we ask, if the program cost your household a total of X dollars, would you vote for or against the program? So in the study, we estimate that the median willingness to pay, the amount that 50% or more of the households was willing to pay, was $30. And aggregated to all US households, that comes out to be $2.8 billion. And that's sometimes called a total value estimate to emphasize the notion that it's including these passive use considerations. And to show you how important the passive use considerations are, Exxon's experts came up with an estimate that was based on just the recreational damages that was only $3.8 million. So that's not the commercial fishing loss, and in the US framework, the commercial fishers have to sue separately, but that's a huge difference. So, we're looking at $2.8 billion versus, Exxon thinking that the damages that they owed the US government and the state of Alaska was $3.8 million. So what was the formal outcome? Exxon ends up settling a case for our $2.8 billion number, which was the largest judgment for natural resources at the time. One of the things that you see, at least in the US with most of these cases, is that they rarely actually go to court. But what did Exxon do? Exxon hired a retired federal judge, and it would have gone to a jury trial. And so they reconstructed a version of our survey. And anyway, in the mock jury trials, basically they always lost. And what would happen is that people would read the survey, the potential jurors would read the survey. It was an easy to understand description of what would happen. And it was easy to understand that there was something that could be done that would have prevented it. And because we're using the median estimate here, they would come up with roughly the $30 number between themselves. And it turned out that the hardest thing to do was to convince them what economists comes naturally, and that is for a pure public good like this, you just take the sort of average or median amount that households are willing to pay and multiply it by the number of households. So if the case had gone to court, they would have argued over how much of the 2.8 billion was for restoration versus response, because the way the US system works is that all of the $2.8 billion had to spend on either restoring things or in natural resource damages, which are used to pay for things that can't be restored. And what you can think of is that you're buying sort of resources that are similar to what was damaged. So we're setting up programs to help the birds reproduce more quickly, and we're buying parkland adjacent to the places that got hit and things like that. So the US Coast Guard uses the settlement to justify regulations to put a prevention and response plan back into effect. And it's very similar to the one in the survey, which is not surprising because we got a lot of that from the original risk assessment. And when you do your job right, what you can see is that nobody ever hears about it. Several years after the Exxon Valdez, a sister ship lost power. One of its two escort tugs pushed it away from a reef next to the one the Exxon Valdez hit. The other one shot at a tow line and pulled it away from the reef. And so anyway, you would have had basically the same type of spill happening again. And with the plan again, nothing happens. And so this settlement dramatically changed the perceived liability in the US for polluters doing harm to the environment. Exxon and the oil companies, of course, didn't like this. And so anyway, they sponsored a conference of their own where they attacked contingent valuation. And in response, the National Oceanic and Atmospheric Administration took a very unusual step of convening what they called a blue ribbon panel to examine the reliability of contingent valuation. It was chaired by two very well-known Nobel laureates in economics, a leading econometrician, a leading micro-theorist, a leading environmental economist, and the US's best known survey expert were the other panel experts. And anyway, it concluded that contingent valuation can produce estimates reliable enough to be the starting point of a judicial process of damage assessment, including lost passive use values. And it made a whole bunch of recommendations that generally followed how we had done the Exxon Valdez study, with two exceptions. The Exxon folks had made a lot out of a claim that the results might not be sensitive to the scope, which you can just think of as how big or small the good is. And there was a standard survey practice that was somewhat controversial, but I'm going to say the survey people generally agreed that it should be done, and that was to include a don't know option. We were able to later show in a paper that you don't need this don't know option, that you can conservatively treat those responses as no's. So following the NOAA Blue Ribbon panel, the oil industry launched a major attack on contingent valuation in the US and actually worldwide, including, running, half-page ads in the Economist magazine and the New York Times. They commissioned lots of academic work. They had a big lobbying effort, and in general, they mounted a campaign that utilized a number of the same organizations and individuals that they had used to claim that cigarettes didn't cause cancer and burning fossil fuels didn't contribute to global warming. But what they did do is they motivated a huge amount of constraint. I should say, this was actually pretty destructive, and you still see some of the, some of the stuff they put out still pops up over and over again. So, but whatever. There was a lot of constructive academic work that followed. We're going to look at temporal reliability, what's known as consequentiality and incentive compatibility. There was a huge amount of work done on this notion of scope sensitivity, both at a theoretical level. Exxon's studies didn't basically hold up to the analysis. There was a recognition that there were lots of scope studies test in earlier studies where they had done. Yes. Actually, hold on. Let me get through this, and then I'll take questions. Anyway,
mute your mics, please. Please mute your mics, all the participants, unless you have a question. Thank you.
Okay. Anyway, it was recognized that there were lots of earlier scope tests that had been out there just because people did split sample studies because they didn't want to contaminate the sample with valuing two different goods when the two different goods were related to each other in some fashion. Then there were a lot of new tests, and they showed that, and this turns out to be important, that there are two sort of key areas where there are scope problems. One was with low-level risk, and that's because people in general just do not deal with small probabilities very well. And the other problem turned out to be with individual endangered species, because what people realized was that to save the endangered species, you couldn't save them species by species. This is where, the people were way smarter than the economists, that you had to save a particular piece of land, preserve it, or you had to set up a marine protected area or whatever. And that tended to do a lot of things simultaneously. There was a lot of development of the theory underlying non-marketed goods. One is on the difference between willingness to pay and willingness to accept. And a big implication there is that if you're measuring willingness to pay and you have what are called sequence effects, those are up here, the willingness to pay numbers are always smaller than the appropriate willingness to accept numbers valued in any sequence. And then there were criticisms that the income elasticity, that willingness to pay was not responsive enough to income. And anyway, we were able to show that that was due to a key misunderstanding of the underlying theory. And this turns out to have big implications for transferring benefit estimates from one country to another, because the standard thing that's done is to just scale them by the difference in income or purchasing power parity or something. And that's typically going to underestimate the number in the lower income country. And anyway, we then showed the implications of a don't know option. And what really makes these surveys different in the standard opinion survey, a lot of people may not know enough to answer the policy question that you're asking, but once they've seen a 30-hour long presentation on the good, you shouldn't really have don't knows. And anyway, there's a way to basically force these folks into into basically treating them as no's, and that turns out to be a very conservative thing to do. So we looked at the temporal reliability in the original study that was done by.
නෑ බේ අපි අද සමාදානේ දාගත්තේ ඉතින් ඔක්කොම අස්සල හිටන් හොදලා සුද්ධ කළා ඔව්
මනමාලිය ඇවිල්ලා මනමාලේ
තනකොළ උනාර ඉස්සරහට කපලෙන් නම් කියලා කිව්වේ මම දැන් ඒවා දැන් තේරුණා
ඔව්
මේ හොදන එකට එවන්න දෙන්නේ
ඔව්
උපුල් ඔයාගේ mic එක on ඔයාට දන්නවද?
Yeah, some people need to mute, but if you want to ask questions, I'm happy to take questions. But let me just get through this slide. One of the key questions that came up was how reliable in a time sense were these things. And so one of the things NOAA did here was the original Exxon Valdez survey, given the randomly assigned cost amounts, 52% voted in favor. And we did an exact replication of the Exxon Valdez survey a year later. And it was done by one of the other big US survey firms, the University of Chicago's National Opinion Research Center. So anyway, one of Weststat's major competitors. And so what you can see here is that, these numbers are just completely stable. And there are other studies that, show when you get big income movements like recessions and things like that, they move. But in general, there's now a lot of work that shows that, over a period like a decade or so, that the numbers from these studies are pretty similar. We also show that the predictive equations for willingness to pay from the two data sets are statistically equivalent. So these, again, these are very different sort of surveys. But let me stop there. If you have questions on the Alaska study, this is perhaps the best known of all the contingent valuation studies, and basically serves as the sort of model of how you would want to do these studies. Okay. So now let's turn to another oil spill study. And I've gotten several questions earlier in talking with people. So this study is in some sense very different from the Exxon Valdez study because it's going to be done before there's any spill. And as often the case, this was done with funding for a prior oil spill legal settlement for a spill that had occurred in San Francisco Bay. And the government, in this case, the oil companies kept saying, one of the really bad things about using these techniques is that we don't know how much it will cost us if there's a spill. And if you think about that, that's what the insurance companies really want to know is what's the cost of a spill, because they back up from that and say, okay, the higher the cost of a spill, the more we will take, precautionary measures to prevent one. And at some point, they may not want to sail particular routes. So the focus here is going to be on California's scenic Central Coast And that was based on the government came to us and said, okay, you've got this money to do a study. We want to post numbers in advance, figure out where there are lots of, not lots, because figure out where there's a reasonable number of medium-sized spills. And what we showed was that there was a lot of barge traffic, some of it small, oil tankers and carrying things like gasoline and diesel fuel and whatever between San Francisco and Los Angeles. Okay, so we picked the place to do, we picked the area to study based on the frequency of which there had been spills in the past and understanding how these spills were happening. The policy question is going to be how much is the California public, so this is this US's largest state, willing to pay in terms of a one-time tax to avoid these medium-sized oil spills from all this barge traffic. And what would this higher cost do? It's going to cover both the spill prevention and containment plans, just sort of like we saw earlier. And this is what happens now when the ships go up and down the coast.
Richard, I think there is a hand up.
Yes.
We can have the question now?
Yeah. Let me finish this line, one line. And the other thing it's going to do, so the first part of this is basically going to prevent spills and contain them in exactly the sort of same way that the Exxon Valdez does. But the other thing that's going to happen is the state of California, on the basis of this study, is going to move these barge routes further offshore and away from places that they think are the most dangerous. Okay, so now I will.
May I ask a question?
Yes. Yes.
Now, in the case of MT New Diamond ship accident, there was a lot of heavy oil released. And also the dead turtles did not appear on the eastern coast of Sri Lanka, but they appeared on the western coast of Sri Lanka. And also, we believe because of the current pattern, deep water currents, which come up from the upwelling areas, the tar balls can come up. Okay, even at a later stage, it can come up.
Yeah, so tar balls are the typical, tar balls are anyway, that's going to happen with these barges that, they're not going to have giant spills like the Exxon Valdez because that's a super tanker, but they're going to leak a fair amount of oil when they have these things. And, sometimes they hit, smaller boats. In other cases, they leave the hatches open or whatever. And so you drop oil and anyway, the result of this is that
in Sri Lanka, the coastal fishery is very important.
Yes.
Especially the filter feeding fish are eaten by people. And also these tar balls can be taken up by these filter feeding fish. So even at a later stage, the small pelagic fish and sometimes semi-demersal fish can get affected by these tar balls.
Right.
And it will it will affect the fishery and also the consumers. So how can we really evaluate the damage, evaluate the loss due to that kind of a reason?
Well, if this is going on a regular basis, just raise that question again after we go through this, because this is designed, any place where there's sort of a lot of ship traffic that's causing the problem that you're talking about, you'll sort of see as we go along. Okay, but it'll take me a couple slides before I get into that. So one of the things that along the way of doing these studies, we're learning more about how to do them. And so all of the current studies put a lot of emphasis on what's known as consequentiality. When people started originally doing these things, they tried to make everything sound really hypothetical. And here, we do the exact opposite. We tell people we're doing this study for the state of California, that there are lots of proposals made for new programs, but the state doesn't want to start the new programs unless taxpayers are willing to pay for them, particular programs. And then we say one way the state does this is it gives people like you information about the program so you can make up your own mind. Then we say your views are useful to the state decision makers in deciding what, if anything, to do about a particular situation. In interviews of this kind, we go to a lot of effort to legitimate both yes votes and no votes. Some people think the program's not needed, others think it is. We want to know what you think. So now we're going to get closer, hopefully, to what you're talking about. We're going to show people again a map of the whole state, and everybody in the US remembers the Exxon Valdez oil spill. So we show people that we're not talking about these big super tankers, because what's going to happen, the big super tankers from Alaska are going to come down and they're either going to go to refineries in the San Francisco Bay Area, or they're going to come down and they're going to go to refineries in the Los Angeles area. So what we tell them is that we're talking about the Central Coast small tanker and barge routes. And so they go between the Los Angeles area and San Francisco. And again, so we're showing them all these sort of islands off here. And this is where we're going to talk about fisheries and things. So note, we've got the whole shoreline here covered. So the gray we're going to show people is rocky shoreline, the yellow is beaches, and the green is marshes. But notice that most of the Central Coast, and including most of the things you see in pictures of California's Central Coast, are rocky shoreline. And what we had done in earlier development work was that we had shown that people are actually willing to pay more to keep the oil off beaches and marshes, wetlands, so that by doing the rocky shoreline, we'd actually come up with a lower bound on the other types of spills. So we show people what the saltwater marshes look like, we show people what the rocky shorelines look like, and we show people what the sandy beaches look like. And now we're going to get into, over time, these studies get sort of better and better at sort of depicting ecosystems in ways that the biologists tend to like. And so again, these birds called murres get to be, they're usually pretty hit. So we're going to tell people what the birds are and how many of the population are. And then, of course, we're going to be, even though this is rocky shoreline, we've got all these sort of small inlets and whatever. So we're showing that, lots of small sea creatures, everything from mussels to crabs and sea urchins and whatever are going to get oiled. And okay. So what's the median California household willingness to pay to prevent these oil spills is $61. So notice that's twice what the Alaska number was. So people are willing to pay a lot more to protect things closer, and more familiar with them. And so California's rocky shoreline is where places like Big Sur and whatever, which are very sort of iconic. We've gotten better here at estimating what the mean willingness to pay is. And so what this did was it said, okay, the value, and what I'm not going to show you is that we're going to tell people how many birds were killed and impacts the fisheries and whatever. And the key thing here is this is not a single spill, but this is a series of spills over 10 years. And so the willingness to pay to put in the response plans and move the ships further offshore and whatever, the value to the public of doing that is going to be about $900 million over a 10-year time horizon. And so the state of California, in consultation with the US Coast Guard and whatever, used the study to assess the adequacy of spill response plans and basically increase them. And then they rerouted the barges further offshore in a lot of areas, in particular areas that were close to the best fishing grounds and where they were most likely to run ground on things. And so as a result of this, once the state of California posted these numbers as what effectively people would have to pay, there've been no major ship spills since this has been done. There have been some pipeline spills because they're not covered by the same legal framework. And anyway, that's just some indication that, again, once you sort of post the numbers like this, the rate at which you get these big, these spills were happening, I'm going to say at the rate of, say 1 a year. There was a good sized spill that would kill a fair number of birds and produce, roll up on shore and produce these tar balls. And so anyway, this is a study looking at a much more routine activity where, there's not one giant accident, but a series of accidents that's statistically at some level reasonably predictable in terms of the frequency at which it's going to happen. And so this is the combination of better response plans, rerouting the barge traffic, and in general, just, when we did the statistical analysis of why this was happening, a lot of it was just not taking enough care. And so that, anyway, once this went into effect, that changed. Okay, questions?
Hello, sir.
Yes?
Actually, I have two questions. One is when you are thinking about that the animal killed due to the ship damage, and do you concern about the natural mortality and normal deaths? Because in our case, sometimes number of animals kills whale and dolphin are very small. And if we have not done proper post-mortem or understand this is what happened due to that our ship accident, then our calculation would be wrong about the number of animal death. And second one is what kind of statistic analysis you use for that analyze the willingness to pay values? Is it the maximum likelihood function?
So let me ask the first question. We had endless conversations with the biologists and this, the lawyers for NOAA and the state of California, because often in these spills, endangered species got killed, but on any particular one of these spills, the answer, if you were to just pull out one of these spills randomly, there would not be endangered species killed. So when we did some development work, we showed that the amounts that people were willing to pay went up if there were endangered species involved. But so I'm trying to remember the exact number. So, what would happen is that, one of these spills, a typical spill, and there were over the course of about 10 years, you would kill about 50,000 of these mures. Okay, so, that was what we were telling people. And so, these were the things that we said, and that you had said, here's how many of these things are sort of being killed over, the 10-year time period. And so we tried to divorce it from an individual spill, and ultimately made the decision not to put the endangered species in, which the lawyers thought, given that the typical spill didn't have them, if they were to use this for trying to collect money from the, it was, it was always difficult to go into court with a number that they could argue was too high.
Excuse me, Richard.
Yes.
There is one person, he cannot, I think he can't mute his mic. Can you do that? You can mute all the mics. When someone raises the hand, you can on it. Because he's disturbing everyone.
Yeah, who is this?
This is Rajapaksa D. Rajapaksad. I sent him messages, but he is not responding. Because you're the administrator, you can do that.
This is RAJ.
Okay, you are muted. Okay.
Okay, I needed it. So anyway, we didn't include endangered species, but that was a big sign. And what you can see is that at some level, it turned out that we didn't need to include endangered species. And that was because, this number, the easy way to think about this is if there was one spill on average every 10 years, that meant that the government was going to go after them for roughly $100 million. And at $100 million a spill, they just cleaned up, they stopped spilling oil because, it's a matter of how much care they were taking. And the combination of, when we looked at these spills, I was surprised 30+% of them were coming because they didn't tighten down the hatches and other things adequately when they left port, and that just stopped. Okay. Other questions? So
just to clarify, I think the previous question, a few questions earlier also, what they were asking me is the long-term impact, say after 5 years, 3 years, 10 years, those kind of impacts, can it be claimed as compensation before or even during those studies or research that is being done? Have you done that before, like for Exxon Valdez or any other accidents?
Say that again. I think I missed the first part. And ask the question again.
Yeah, actually the impacts, some of the impacts are immediate and easy to identify and compensate. But as some of the questions that came up, some of the impacts are long-term impacts, which have to be studied over a long period, maybe years, 10 years, 5 years, like that.
Right. So
is it possible to get compensation or cost recovery for those? Has it been done before?
Well, I mean, let me say that if we were to look at, say, the Alaska spill, I mean, they had estimated on some of the things like the pods of whales and some of the birds that we showed people and gave them population numbers on, that the recovery time was well in excess of 20 years. So the answer is, if you think about the Exxon Valdez, what we're doing, Spill, is we're getting what people are willing to pay to prevent the spill from happening. or I should say, prevent a similar spill from happening in the future. And because we tell them what the injuries from that type of spill are, and that they would have long-lasting impacts on the population, the answer then is yes, you're getting compensation for the fact that these injuries are going on for a long time. And you could also see that in the Montrose survey, that what people are doing there is people are explicitly valuing speeding up natural recovery. So both of those, you know, in those cases, those are, you know, those are dealing with long-term injuries in different ways. This one doesn't have a really sort of a long-term notion. That you know, what we depict when we show people various pictures here are just these, you know, barges and small tankers that are running, you know, up and down the coast, and you know, the typical leakage from these things was, you know, 1,000 barrels, 10,000 barrels, 20,000 barrels, but not hundreds of thousands of barrels. So what we represented here was a series of spills, all of which caused injuries over, you know, that would last in some sense a few years for the populations to recover and, you know, to clean, you know, the tar balls and that sort of stuff up. So this one doesn't, but the Exxon Valdez and the Montrose study explicitly address this long recovery time in different ways.
So was the research
actually-
funded by, was the
Yes.
research on this funded, or is it, did the ship owners pay compensation for the results or for the research?
Well, in the case of let me say that in the case of this study, the owners of a big oil refinery in the San Francisco Bay who had a major leakage, as part of the settlement there, they agreed to pay for a study, this study that would look at, you know, harm on the Central Coast, because, you know, what was happening there was that they were refining different products and loading it on these barges and small tankers, you know, and sending it up and down the coast, because they were serving all these cities between San Francisco and Los Angeles. And so that was a natural thing to say is, okay, you know, you did this harm in the San Francisco Bay, but the oil products that you're manufacturing are going up and down the Central Coast. And so as part of the settlement for that case, they agreed to fund this study. And that was a way, and that's not uncommon. Lots of these legal settlements, and I'm going to say even more so on the science side, lots of these legal settlements involve, you know, funding quite large, you know, long-term monitoring programs.
Actually, when there is actually evidence that especially due to this heavy oil, there were turtle deaths, and actually there were deaths of different animals. So actually we were expected to identify that this happened due to the oil spill from this particular ship. And especially in the case of small pelagic fish, like the what you call sardines, and also the semi-demersal fish like pony fish. Now, for the small scale fishes, these fish are very important. And
Yes,
when
so-
they take the oil, you will get the taste of oil in this fish. Okay, even after a long time, you will get this taste. But then how can we claim that this oil came from this particular ship? Sometimes they might say, because there is a shipping route around Sri Lanka, that can be a result of oil released from some other ship. So how can we know that this is the cause for this kind of a result. But
Well,
when we are claiming, we have to prove that it came from this particular ship. So have you really heard of any incident where this kind of a problem is tackled?
yes. So let me say that in the BP Deepwater Horizon oil spill, one of the claims British Petroleum made was that there was a huge amount of oil from leaking oil wells throughout the Gulf of Mexico. And so they wanted to claim that lots of the injuries were not due to their oil. Okay, and so there's chemical analysis. There was a huge amount of chemical analysis done of, you know, the oil coming out of the BP oil well. And fortunately, in that case, they had drilled a deep enough well that they had hit oil that had a different chemical fingerprint than most of the oil wells, you know, in the Gulf of Mexico were much shallower. And I don't know that they would have registered differently, but there were lots of modelers who modeled where the oil spill went. And again, in the US, commercial fishing injuries are different. The commercial fishing fleets have to sue separately, and that's an odd nature of US law, but there was a federal court decision that decided that the government was the trustee for recreational fishing, but that the commercial fishers were private parties that could organize as what they called a class. And so in all of these cases involving commercial fishing in the US, the government is typically not involved, although they often help them out on the science side. And I haven't worked for the commercial fishing folks, but I've had friends who have been their economic experts. And so there's definitely a literature on trying to sort this out. And the oily, you know, we'll see as we go on later, their techniques for dealing with the notion that the fish from a particular location are contaminated with oil and taste oily. And that's a somewhat different problem from saying, you know, you've got this large issue here that, you know, that in the Alaska case, you were inherently trying to take the oil out of this, you know, frigid northern place with icebergs. And, you know, the question there was, how much did you want to spend? And what we showed on the benefit cost ratio for the Exxon Valdez study is that the benefits were almost 10 times what the costs were, because the response plan was costing the oil companies about $40 million a year. So that's about 400 million over 10 years. And so you can see why they didn't want to pay, you know, for the $400 million every year. But once they were looking at, you know, a $2.8 billion expenditure, that looked like a real bargain. And anyway, this is dealing with closer to the same problem, but this is a way that if you've got, you know, a lot of ship traffic on a particular route, and you're getting the same type of accident with some frequency, you can in some sense do a study. And, you know, what the lawyers were planning to do was to just say, look, you know, this is $900 million over 10 years, and they're roughly, you know, 10 spills. So, you know, we're going to charge them $90 million a spill. And, you know, once they posted it, you know, the ships just got a lot safer. And that's the general result that happens. after the Exxon Valdez and the oil pollution, after the Exxon Valdez settlement, there has not been, again, another major uncontained giant oil spill from a supertanker, you know, since 1992, when we did the study. So that's the BP oil spill, again, was from a oil platform, and that was governed by a completely different set of liability standards. And again, they were just really sloppy. If they had known that they were facing the liability that they were, they probably wouldn't have taken the risk that they had. They would have shut down the well before they had their accident. And their response plan, they had just copied from Alaska. So, you know, it had all sorts of, you know, Alaska marine sea creatures in it. So, you know, this is just, companies respond to the, you know, economic incentives of having to pay for these things by getting a lot safer. Okay, now we're going to look at a variation on contingent valuation, and this is probably the most common variant of contingent valuation that's currently used. This is called a discrete choice experiment, and in contrast to the three sort of big contingent valuation surveys that I showed you earlier, they're only going to have a status quo alternative. They're only going to have people choosing between the current status quo baseline and an alternative, which can have a whole bunch of attributes, but there are only two choices and there's only one choice question. So what you can see is that format is the simplest version of what's called a discrete choice experiment. Discrete choice experiments typically have, they typically either ask people more than one choice question or have more than one alternative, and they're characterized by having a number of alternatives, attributes that vary across those. So here we're going to look at valuing poaching and logging in tropical forest ecosystems. So this is a paper that I did with Jeff Vincent, who's at Duke University and was in the proceedings of the National Academy of Sciences in 2014. So our study site is going to be northern Malaysia. This is going to be the last giant unprotected tract of tropical rainforest basically in Asia. And most of the population in Malaysia lives in the greater Kuala Lumpur area. And so we decided to do three big samples that are stratified into three. I mean, we're going to have one big sample that's stratified into three subsamples: urban, suburban, and rural. So the urban is the city of Kuala Lumpur to begin with, and Kuala Lumpur is surrounded by a particular county, and we split it into two parts, suburban and rural. But again, we do lots of extensive survey development work. So like all of the ones that we're showing, you usually start people out with this map. So this is known as the Bellum forest map complex. This is sometimes typically referred to as the Royal Bellum area. And anyway, it's actually bigger here, but anyway, it's up on the Thai border with Thailand, and it's in a state in Malaysia called Perak. And so we show people where Kuala Lumpur is, and this is the state of Perak. And the state of Perak is going to be important because we're going to show them these forests, and what happens is you cut down the forest, you actually increase the chance of flooding in the sort of area around Kuala Lumpur. Okay, so respondents are going to be given a description of the forest complex and policy options. The options are going to be described in terms of these features, which in the technical jargon are known as attributes. The number of hectares logged, either the entire sort of forest complex, which is all, half of it, or none of it. And we, of course, tell people how many hectares that is. The number of hectares that we're going to protect from poaching, either all of the area, half the area, or none. The number of floods in Perak that are directly tied to logging. The number of jobs that are created from the logging. These are not jobs in Kuala Lumpur, but these are jobs in Perak. And a sort of an odd notion here is that the folks with strong environmental leanings are going to be the ones who care about people in Perak not having as many jobs. And then we're going to have the cost to households in terms of higher water bills in the Kuala Lumpur area that people would pay. So there's always going to be one option that's no cost. So you can think that we're going to have this status quo option where we're going to log the forest and people aren't going to pay things. So everybody's going to get 3 options: the status quo management option and 2 alternatives, and they're going to be given 4 separate choice sets. So we tell people, and this turned out to be the key sort of issue here, and we did this with the Harvard biology department. Nobody had ever figured out how to sort of separate out what happens with logging versus poaching. And so anyway, we listened to biologists, and we said, what would happen if you cut down all the trees? And so they said, these are the species that are going to disappear if you cut down all the trees. And what tends to happen is the big animals tend to move out of the areas that are being logged, but the big animals are getting poached, and it turns out that you need different policies to deal with logging versus poaching, because logging is typically going to be legal, and poaching requires game wardens and things like that. So anyway, if you did nothing, there are going to be 4 to 6 floods. You're going to create 7,500 jobs to log all the forest. And if the government does nothing, there's no cost to you or the government. So this is the second one. So in the first card, people saw policy A and B. So this is the second of the 4 choice sets that this particular respondent sees. So we tell them under logging that we're going to log 300,000 hectares. That's the whole area. Under policy D, 1,500 hectares. And under the no protection status quo, we're going to log all of it. And again, different people are going to, I should say, this attribute, the status quo attribute, the status quo column is always going to be here because it's the sort of constant alternative. And that's what you need to include in these to get people to be comparing things to the same utility level. And this utility level has to be feasible. And to be feasible here, that means you can't increase the cost on people. So you can see that policy, anyway, these policies differ by how much you log. They're going to differ by which species go extinct in policy C, because you're logging everything. All these species are going to go extinct, half of them extinct here. And with poaching, you're going to get this different set of species. And again, you're going to get the poaching expressed both in terms of the number of hectares that would be protected. So note we're going to log, and so we're never logging the entire area. We're logging 300,000 hectares, which is a pretty good size chunk of it. But with rigorous policy protecting poaching, then none of these animals are going to go extinct. Here, you're going to protect 1,500 hectares, and so half of them are going to go extinct. Then we're going to change you get variation in the number of floods, you get jobs created in Perak, and you get in Malaysian currency the cost per month in terms of the water bills. So now instead of being able to use instead of being able to use the really sort of simple estimators we saw with the binary discrete choice contingent valuation studies, you have to use some type of logit model. And here we're just going to show you the results from a simple conditional logit model. This is just a multinomial logit model. In the paper itself, we have more general models, but what you can see here is that the higher the cost to people, the less likely they are to choose things. And you can see that there's a difference in the price coefficient across the three different, the city of Kuala Lumpur, suburban, the state of Selangor, and the rural part of the state. You can see that they have virtually identical preferences, though, in terms of reducing logging. And remember, logging is going to save the one type of species. The next thing here you can see is that in general, well, I should say uniformly preventing poaching is not as important to people as preventing logging, but there's quite a difference in the rural areas on poaching. And then you can see that the jobs coefficient is not significant. So that what that's saying is on average, people care about jobs, but the numbers are sort of small, positive, and insignificant. And it's only after you sort of interact the jobs attribute with environmentalists, you see that there's a group who care about the jobs. And so down here, one of the things that was the most interesting was what's the ratio, and in these discrete choice experiments, what you're usually trying to do is you're trying to figure out what's the optimal configuration of these attributes. Or often the government is looking at not one policy versus the status quo, which is the typical setup in the canonical contingent valuation framework. They're considering a lot of different policies. And so one of the things that happens there is you want to know, how do people trade off logging versus poaching? And so on average, you can see that preventing logging, is basically 49% more important than poaching. But there's a lot of variation. It's a lot closer to one in this, in the city of Kuala Lumpur, and in the urban areas, it's almost twice as important. We're also going to get the willingness to pay for changes in these attributes. And so this is the mean willingness to pay in ringgits per month in terms of their water bill for this change in logging. And you can see there's some variation. For instance, you can see that the willingness to pay for poaching is actually substantially higher in the suburban areas than either the city or the rural area. Okay, questions about this? So
yeah, Richard, this is I think this is just based on the MNL model, maybe.
To
capture the unobserved heterogeneity among the respondents, maybe the RPL or the latent class.
Yeah, so there's a pretty fancy mixed logit model in the paper. So I've just displayed this one because it's really simple, but you don't, let me say that if all you're interested in are the averages, the conditional logent model is going to give you, the marketing people showed a long time ago, if all you're interested sort of is in aggregate market shares, which is what you could think of as the fraction supporting different, different options. Those are pretty well estimated by a conditional logent model. What happens is if you want to get into what's the distribution of income elasticities, or what's the distribution of willingness to pay for logging. So if this 6 ringgits per month is the average amount, fitting one of these mixed logent models is going to give you what the distribution of this looks like. And that's actually pretty interesting, particularly across the 3 geographic areas. So in these studies, if you're, a lot of the interest is in, what are the differences across, people and types of people. Anyway, this data is very sort of rich in terms of what you can potentially do with it. And I just want to emphasize that this is probably the most common variant of contingent valuation. In fact, there are tons of things which argue that there's sort of a difference between contingent valuation and this. And Jordan Louvier and I have a paper where we argue that that's not correct. And when you look at this, you can say, well, why are people doing this? If the government is considering lots of policy options and you're sort of trying to fine tune things, or let's say you're looking at the California oil spill study, and what you want to do is to say, hey, everyone, the different scenarios are going to impact different sets of birds and different sets of shoreline and whatever. Then you can make those the attributes, and then you can use this model for lots of different types of accidents and things, instead of tailoring, one big study to one particular accident or possible accident. And there's some drawbacks to this. You can show that the binary discrete choice contingent valuation study that we looked at in Montrose or California Oil or Alaska or the BP, that's the way to do things in the completely most defensible way. But that's because you're only collecting one response per person on a binary choice. You're just, on a per survey basis, you're not collecting much information, and so you're paying a lot for that information. Okay, so most things that government agencies around the world do, because they're typically interested in multiple policy options or multiple sort of things that could happen, currently take this format. And so what you see is that, for instance, the US government is probably only going to employ the sort of thing that we saw in the Montrose study and the Alaska study, in really big cases like the BP Deepwater Horizon study, where we got a $14 billion settlement. When there's a lot of money at stake and you have to nail everything down perfectly. Okay. Any more questions that people want to raise? So let's have a little bit, we're going to have a little bit more discussion of contingent valuation issues, and then we will take a break when we get to the other non-market valuation issues. So let's think about, we've just been talking about this issue. sort of a general discrete choice experiment versus what's known as a binary discrete choice contingent valuation question. So the binary discrete choice CV question is the simplest version of a discrete choice experiment. There's a single status quo versus a single alternative, and there's one choice set. It has the best incentive properties. In fact, the binary discrete choice question is the only one where you can show under a set of auxiliary conditions that respondents have an incentive to truthfully reveal their preferences. The binary choice thing here turns out that there are all sorts of simple models that you can use where you don't have to make any sort of assumptions. And most of the sort of more general discrete choice experiments are these days fit with sort of very complicated logit type models. The other thing to think about is that any discrete choice experiment, no matter how many alternatives and how many choice sets and how many attributes you've got, can be implemented as a set. And this is what Jordan Olivier and I used. So it's actually a paper in environmental and resource economics, which has gotten to be pretty highly cited in terms of coming up with a typology of how all the different ways to ask these questions fit together. And the way you do that proof is to show that no matter how general your discrete choice experiment is in terms of how many alternatives, how many choice sets, and how many attributes, you can always implement those as single binary discrete choice contingent valuation questions with an independent sample. And the difference is that you get, let's see this, sorry. Fix that, not internal. Is that you're going to get internal scope tests that's sometimes called within subject versus external scope tests. And the external scope tests are just way harder to pass. And so a lot of the development work in the really big contingent valuation surveys is to say, hey, I'm not going to be able to show people that there are, several different levels of these things. I'm going to have to describe it so accurately that people don't need to be able to, directly compare them. And a lot of people have actually said, well, that's actually the reality. When you go to the store and you see the products, you see what you can buy. You don't have to make sort of choices between two things, not knowing what everything looks like. So the main reason people use these discrete choice, more general discrete choice experiments is that they're just dramatically cheaper in terms of the cost for how much information you get about the attributes. And they're again, just really important when you're considering a range of policy options. And in general, and I don't know what the case is in Sri Lanka, but more and more of these are being implemented with online panels where people are taking these surveys using their cell phones or computers. And that has some obvious sampling issues, but for instance, I've just done a couple pretty sizable surveys in India doing discrete choice experiments with online panels that are run by a big international survey company called YouGov. Okay, one of the things that has just radically changed how environmental economists tend to look at these things is in 2007, Ted Groves, and who's a major micro theorist, and I wrote a paper, And what we showed was that for the response to contingent valuation survey to be interpretable as revealed economic behavior, the respondent needed to perceive it as consequential, which meant that it potentially influenced a policy that the respondent cared about. And once the survey becomes consequential, it's no different than any other sort of revealed behavior of a respondent. I should say, no, of an agent. And for it to be incentive compatible, which it means that it has to be in the self-interest of the respondent to truthfully reveal their preferences. And so to do that, you need a single binary discrete choice question with a take it or leave it offer influencing a single issue. And yeah, I needed the other part of this. Anyway, you need a single binary discrete choice question, and you have to have a coercive payment mechanism. And this turned out to be the key to understanding why marketing surveys for new goods overestimate, marketing surveys for existing goods actually underestimate, in that they estimate a higher price elasticity. So, and if you thought about voluntary contributions, it violates the coercive payment mechanism. One of the things in the discrete choice experiment, the more general ones, is under a reasonable set of assumptions, we've shown that even if total willingness to pay is not unbiased, the marginal trade-offs between attributes tend to be. And for a lot of policies, that's all that you really need, is how people are trading off things on the margin, and the total willingness to pay, which turns out to be important for these lawsuits where you're trying to get the companies to pay the total willingness to pay amount. You know, that's where the bias problem comes in. But what we show is that the bias actually cancels out and when you do these trade-offs between attributes, because we show where it shows up. Okay, we've talked a lot about the role of development work, but the key to making these things work is just making people understand them, using a lot of visual aids, figuring out how people think about them, figuring out how to deal with divergent beliefs. People often don't trust the government to either deliver the good or to only collect the amount. Doing it, and the people who do these studies, they can look at your contingent valuation instrument without your collecting any data and give you a pretty good idea of how well it's going to work. And anyway, it's these survey instruments, if you do the development work, they're often really useful, even if you never collect data for the main study. And in lots of government agencies, the surprising thing is that the decision makers sort of at the upper middle sort of decision makers who have to decide, make the policy decisions, they often ask for the contingent valuation, discrete choice experiment survey instrument, because what's going to happen there? All the science knowledge is going to be embodied in a way which is understandable. And you have to think, as you go up, at least in the US, most of these people are lawyers rather than economists, or scientists. And, they just read these things rather than, the stack of technical documents which they don't understand. And so all that's sort of known about the decision can get embedded in one of these things. Okay. There are lots of critiques of contingent valuation. Its use, it remains quite controversial. And that's in large part because what it really does, in particular, because it's collecting the fact that people are willing to pay to improve the environment, even though they're not directly using a lot of these goods. So by increasing the economic value, all the polluters basically, you know, they do not like this notion at all. And so everywhere that surveys are used, they get attacked. Our experience, though, has been it does not matter what technique you use. If you're mounting a lawsuit against a company and you're trying to, you know, get any sizable amount of money from them, they will attack whatever techniques you do use. And, you know, that's coming from having used, we'll talk about other techniques here in a while, but we've been involved in cases where you know, there are different techniques that are obviously the most appropriate for different situations. And our experience is that you get attacked for whatever you do. But critics raise a range of possible problems. The first is what they call hypothetical bias, which is some notion, we're not quite clear exactly what hypothetical bias is, but supposedly it stems from the fact that we're asking people about these policies and surveys. And supposedly the bias is upward. In general, it's possible to show that the bias is downward, except in some cases, if you ask, for instance, for voluntary contributions, and you follow the Carson and Groves framework, what you show there is that if the surveys aren't consequential, or we should put this in a slightly different way. If you ask a voluntary payment mechanism in a contingent valuation question, the only effect that the only thing the contingent valuation survey can do is increase the likelihood that whatever fundraising mechanism is in the survey with the voluntary contributions is actually implemented. So we show that the optimal behavior in that case is to over pledge in the survey, and then to actually free ride, that is contribute less than you said in the survey, if you actually mount the fundraising drive. And that's because this is just sort of the classic economic free riding, that for any sort of public good, you would like to enjoy it, but get the other people to pay for it. So anyway, it is possible to come up with situations where you're going to predict hypothetical bias, but this is, anyway, this is a catch-all that's sort of thrown out there. Another is that preferences for unfamiliar goods may be ill-defined, and that's a very legitimate concern for the standard public opinion survey asking about a policy issue. But what I hope I've convinced you here is that, you know, these surveys are really detailed. And so these goods, you know, after the survey should no longer be unfamiliar. And in that sense, people should now have preferences that are well-defined in an economic sense because they know exactly what they're doing. And what we show is that, you know, the amount of time that people devote to making a decision of a similar cost amount is generally, you know, they're devoting more time in the contingent valuation survey than they do to most marketed goods that they would buy of the same cost. You can say that they're basically saying yes to please the interviewer due to some social desirability effect. We've run studies that show that that's not the case, and clearly if you're doing these things online, which is the cost-effective way to do this, there's no interviewer anymore. there's a notion that the values are just due to the fact that people want to do something good for the environment. This is sometimes referred to as warm glow. There's something to this, but it turns out not to be relevant for accidents. Because what happens in an accident is that the accident defines the warm glow in some sense comes from a sequencing problem, and that is people may want to improve the environment, and if there are several different options for doing so, then there's substitution between those options. But once you enter into a damage assessment framework, you're in a situation where you've already picked the accident as the option. There's some arguments that claim that the findings don't conform to theoretical predictions. There's been a lot of work showing that most of these had the theory wrong. Another issue that comes out is that the willingness to pay estimates are definitely sensitive to context. People have very strong preferences over the types of taxes they pay. They trust or don't trust different types of government agencies and providers in terms of doing this. And both of these make sort of perfect sense. If you don't trust, a government agency to actually provide the good, what should happen? Your willingness to pay should be lower because you should reduce your willingness to pay by, proportionate to the likelihood that you get the good. So, the people who look at these things say, everybody in public finance knows that people care about the tax mechanism. And when you work through, some of the other ones, if you weren't seeing claims, if you weren't seeing differences based on the probability of provision, that would be bad. There's some claims that the revealed preference estimates are in some way different. That usually comes from cherry picking, selectively picking a few of the estimates. Years and years ago, we compiled 616 comparisons of contingent valuation versus various revealed preference estimates and showed on average the contingent valuation estimates were a little bit smaller and highly correlated. And that demonstration has been done over and over again for specific types of goods. But it's always possible to pick out some studies where that's not the case. We now know that the survey should overestimate for new private goods, because if you say yes for a good that's not yet produced, all that's going to happen is that you're going to make it more likely that the good is produced and you get to decide later. And for voluntary contributions, you get something similar. So anyway, as I said, there's lots of controversy. The polluters complain about all of this stuff, and most all of this stuff is now worked out fairly well in the literature. Okay.
Can I ask a question, please?
Yes, ask questions.
Yeah. Regarding the arguments, the theory may argue the RP produced the lower bound of the stated preference, but in the empirical studies argue in both in some studies. So can you just explain something about this argument's lower bound or the upper bound?
Well, so what happens is if you have an accident, you destroy something. And the correct property right in that case is how much the public would have voluntarily taken in terms of compensation to let that happen. So theoretically, for going back to 1976, a paper by Robert Willig, you knew that willingness to accept compensation always had to be bigger than willingness to pay. And then there's a paper in the American Economic Review in 1992 by Michael Hanneman that shows for quantity constrained goods, which was one of Hicks's 4 cases, that this difference can be quite large. And the reason for that is that you as a person can't go out and easily change the quantity of the environmental good that you're buying. And so those differences are quite large. And then there's another paper that I wrote with Nick Flores, who's the econ department chair at the University of Colorado, and Michael Hanneman, where we show that in a sequence, so one of the things that critics do is to say, hey, there are a whole bunch of things that people could buy. And what you can always do in a sequence is show that as you increase the number of things that people can buy, and you put them in some order, the further out in an order, the further out you get in the order, the lower the willingness to pay for any particular good. But what we show in that paper is that the opposite happens with willingness to accept compensation. So in a willingness to accept compensation sequence, at every step in the sequence, you're destroying more and more environmental goods. And at each step in the sequence, you're giving people more and more income. So people are getting richer and they have fewer and fewer environmental goods so that the ones that they have are more valuable. And what we do there is we show that in some sense, willingness to pay derived first in a sequence as if it were the only thing that was, being offered, is always less than a willingness to accept number in any sequence. And so that's sort of the theoretical proof that, at least used in a damage assessment context, that you don't need to worry about these so-called sequence order effects and the goods not conforming to theoretical predictions. Did that answer the question?
Yes, but actually, I just want to clarify the reveal preference, the lower bound of the estimates of the reveal preference and the stated preference. The reveal preference, because theoretically that does not capture the disutility. So that may reveal preference may be estimates is the lower bound of the stated preference, but the empirical results argue in the both places.
So if we're talking about the revealed preference estimates, what you can show there, let's say we can pick and usually most of the revealed preference estimates are, for instance, involving these quasi-public goods that we'll talk a fair amount about in a little while, where they're provided by the government. They often have a price. You can observe demand for them. And the problem with a pure public good is that they're not really much in the way of revealed preference estimates out there that are directly sort of comparable. So we could look at people going to, forest campgrounds where whatever the government agency running the, parks or whatever has an entrance fee or a camping fee. And in those cases, you can easily get revealed preference estimates, but you can easily structure contingent valuation estimates that are almost identical. Okay. And in those cases, you would expect those estimates to be similar. And that's where we went and we searched for comparisons where the revealed preference estimates and the contingent valuation estimates should be estimating roughly the same thing. And in those cases, what you show is that on average, the contingent valuation estimates are a little bit smaller. I mean, you know, we're talking maybe 10% smaller, and you know, the correlation between the estimates is like 0.6. And these estimates are a lot noisier than you know, you might think. A lot of science estimates get more precise, and the estimates are noisy because there's just a lot of preference heterogeneity in the population. Then there's a different case, and that's where the contingent valuation estimate should include a fairly sizable, or potentially includes a fairly sizable passive use component. In that case, the contingent valuation estimate should be a lot larger. So, for instance, we could compare a travel cost estimate for closing the fishery sites in Alaska that were impacted by the spill, to the contingent valuation estimate, and you should get an enormous, you potentially should get a very different number, because think about what's happening in the travel cost model. The only people who are being counted in the travel cost model are the people who are actually fishing in Alaska, or potentially fishing in Alaska in the impacted area. So contingent valuation estimates in a lot of instances and theoretically, you know, should or potentially should be a lot bigger. But it's not that hard to find comparisons where the two approaches should be quite similar. And the best thing to look at it, and people run these fairly often, at least in the US, because a lot of things are on the ballot for people to vote on. What you can show is that the surveys to predict how people are going to vote on the ballot propositions that are done fairly close to the election, you know, on average, they're all somewhere between about 2% and 4% across hundreds of these ballot propositions every year in the US. And when you do contingent valuation surveys, if you give people the same amount of information that they see on the ballot proposition, you get almost exactly the same answer as the actual vote. So, you know, this is the case where, you know, again, if I wanted to make contingent valuation look bad, I could certainly find comparisons that do not look good. And often those comparisons come from exactly the same survey instrument, because it's not uncommon, for instance, if we look at the recreation case, to collect information about what people were doing with respect to information in the past. And you can use that to estimate a travel cost model that we'll talk about in just a minute, versus the contingent valuation study, which is going to look at, you know, potential changes to the fishing environment in the future. And so those are compared fairly often. And when you see big differences there, you know, usually you want to figure out what it is. There was a study years ago where, anyway, there was a notion that the contingent valuation estimate was a lot bigger. And anyway, it was a hunting example, and it turned out that in that case, what you needed to do was to, include in the travel cost model, the probability of actually, shooting one of these animals or whatever. And, once you did that, the two estimates were pretty close. So when you see differences there, it's usually that you're either measuring different things or that something has gone astray in the modeling. Okay. Anyway, any more questions? So this is like the perfect stopping point. We're almost exactly at 2 hours.
Now, in the case of, now I'm not talking about oil, I'm talking about plastic. Now, plastic can get deposited on the shores, and also the microplastic can, nanoplastic, especially microplastic, can get settled on the rocks. Now, especially now in Sri Lanka, there are two types of winds, especially in the southern region, the western coast, the people in the coastline are affected by these winds. And this small plastic can get carried into the land. And if people inhale it, there can be a lot of lung problems. Now, if actually now still the plastic is coming, okay? So there is a big possibility that these small pieces of plastic will get traveled with the wind. So how can we now, if there are any health hazards due to plastic, how can we really claim for that? Now, people say, especially in the people in the western coast, they say they have all different sorts of problems. And also they believe that there were several deaths, and they think that it is due to something came from the ship. Especially during the fire, there were noxious gases released. So people say that some of these things may have affected them. So now there is a problem with plastic, which can cause long-term effects. And these effects may not be actually easily visible, but there can be impacts. So how can we really account for this kind of problems, especially with respect to human health?
Okay, well, there are a whole bunch of questions there. So let me answer the simplest one here. There are a fairly sizable number, by sizable, maybe 20 studies that measure what's called cleaning up marine debris. And some of these studies, the ones that I'm familiar with, are in the US, but I've seen, I think they're Australian studies, and I think they're Japanese studies and whatever. So it's not uncommon for, and plastics is the big thing, but all sorts of stuff from whatever, marine, all sorts of stuff washes. All sorts of stuff washes up on the shoreline. And so you can certainly do two types of studies. You can do contingent valuation studies on what is the willingness to pay to clean up all this junk on the beaches. And there are interesting variations on that, because in addition to how much people are actually willingness to pay, which is income constrained, you can get people to volunteer. You can ask people how much time they would volunteer to do this. And so volunteer time in a lot of places, there are a number of places that have, this is beach cleanup day. So anyway, there are a bunch of studies that value, getting the marine debris off the things. Now, none of these, as far as I know, look at microplastics. These are like plastic bottles and plastic bags and, plastic drink can, the round things that hold 6 packs of drinks together. And so there are these marine debris studies, contingent valuation studies. There are also travel cost studies that show that once you get a lot of marine debris, particularly people who go sunbathing or beach swimming, that beaches with a lot of marine debris just really are not nearly as attractive. And that's why anytime there's a lot of tourism involved, whether it's local or foreign, there's a lot of effort to clean up the beaches. And some of that, if you look and say, why are governments in some places spending money to do that? They do these marine debris studies, and what they show is that visitation rates, once you get a lot of this plastic covering beaches, recreation goes way down. There are also a small number of hedonic pricing studies that show that, again, once the beaches sort of and shorelines start getting marine debris, then the rental rates on tourism property starts to also fall. Okay, so all of those are just saying, if the problem is just generic, highly visible plastic, all sorts of other junk that washes up from ships, all the methods that we've just talked about, for instance, the discrete choice experiment approach, if we were to go back up to sort of it here in some fashion, we would say, which of these places would you go to visit, to go for a beach day, and we would describe different attributes, and one of the attributes would be how much plastic, and we would show people what the picture, what these beaches look like. And so Carrie Smith at Arizona State University did some of the early beach marine debris studies. So the health problems are a different thing. And the way to deal with the health problems is with what we're going to talk about next, which is a production function approach. So if it's, if we're just talking about visibly cleaning all this stuff up, then the discrete choice experiment approach that we just were talking about, and the travel cost approach or hedonic pricing approach, both of which we're going to talk about in a little while, will work. The way to deal with the health issues is probably a lot harder, but I'll describe, raise that again after I go through the production function approach. Okay.
Okay. Thank you very much, Richard. So we'll have a break now.
Yeah.
About how many? 15 minutes is okay?
15 minutes is good.
Okay. We'll come back Sri Lanka time 11:10. Okay.
Okay.
At 15 minutes. Okay. Okay. Thank you, everyone.
Thanks.
We'll have a small break.
Okay.
Okay. Bye. Richard, if you are ready, we can start.
Yep. Okay. Sharing. Let me start sharing again. Print slide. Okay. The next thing we're going to do is we're going to talk about the production function approach, and what it's going to do is it's going to take an ecosystem service and treat it as an unpriced input to a production function. And we can think that a production function is basically a purely technical relationship. So, you know, the classic production function would be, you know, I use so much land and I use so much fertilizer and so much seed and so much water and whatever, and I'm going to grow an agricultural crop. Lots of epidemiology relationships, fishery, population dynamics are all sort of special cases of these production functions. There's another function that comes into play called a cost function, and that's just going to describe the cost of the market inputs that you use. And then there's something called a profit function. And what's the profit function going to do? It's going to multiply the output from your production function times market value, and it's going to subtract off the cost function. And you're going to choose the marketed inputs to maximize profits. So this is where the microplastic example is going to could come in. If the good doesn't have a market price, then oftentimes if what you're doing, if the production function is saving time, then you use whatever your government thinks is the official value of time. If it's saving lives, then most lots of government agencies have a statistical value of life. If it's saving morbidity, you know, there's usually a value for it. And so for lots of things, you know, you don't actually have to have the actual revenue. If you have the actual revenue, we'll see what happens. But anyway, sometimes the production function approach in a non-market valuation sense is referred to as a two-step sort of notion. You basically maximize this and you take the unit value for whatever the thing is from some second source. And that could be another sort of non-market valuation study. Let's see how this works. So what is the profit function? Profit is just revenue minus cost. We'll assume that the markets are competitive. So that's just P times Q. And we'll think we only have one input like labor. So this is just the wage of labor. And we have a technical relationship. We're going to substitute in the Q this technical production function. And so it's going to be alpha. Remember, we're using X, so it's going to have a coefficient. And this is just what's known as a Cobb-Douglas production function. And the environmental input is going to be E, and it's going to have a coefficient. So what do? We do the usual sort of calculus thing, is that we maximize profits by setting the derivative of the profit function with respect to X. In the simple case, we only have one input equal to 0. You just get this relationship. You solve the math. You say, this is how much your workers, if that's the only input, should get paid. And this should be interesting right here, because what this is saying is that the better your environmental quality, the more the workers are going to make. Okay. And so the key thing here is that both your profits and the return to the other factors, which you could have multiple of, are going to depend on this environmental quality measure, even though this environmental quality measure is not something that you can buy and sell. It could simply, in our agricultural example, be the sort of temperature where you're trying to grow the crop. And all that you're going to do is you're going to have a productivity parameter that says how much more production you get as the temperature changes. So the key thing here is that the environmental attribute is going to influence production, but it's not under the firm's control. But we can ask the question, what's going to happen to profits for our good farmer here if we switch the environmental quality from the initial status quo level? And here, instead of temperature, we could think this is the water quality input. If in a fishing example, this might be pollution of some sort. So if we shift the environmental quality from its original level to a new level, then what we're going to do is the amount of hired inputs that you do is going to change, how much you pay them is going to change, and your profits are going to change. So if you're just looking at this from the firm's level, the difference in profits is the economic value for the change from the environmental quality level E0 to E1. And so if we were just doing this for farms or fishing boats and whatever, and we, improve water quality in some fashion, what's going to happen in this is the profits are going to go up, the workers are going to get more money as a result of that. And so anyway, that's pretty straightforward. And if we think about the plastic example, let's say that we have, a value of whatever health problem, we have a value for whatever health problem the plastics may be causing. And so what's going to happen is that we're going to have some function here which produces health, and it's going to shift up and down by how much microplastics there are. So we have a way to value it. And this is what people are, this is just the rest of people's budgets. And anyway, that would then give you estimates that, so the production function here is going to be estimated under two or more. Actually, to estimate the gamma parameter, you'd have to have a whole bunch of different plastics levels. And anyway, you're going to get health out of this. And then you're going to have you're going to take from the literature someplace an estimate, instead of the price of the good, the estimated value of the sort of health change, and subtract off the cost of supplying that. But that's a way to do that. This is a really common thing. For instance, there are papers on climate change that look and say, okay, what's going to be the big adaptation as the temperature gets higher? And it's basically that air conditioning use is one way to mitigate that. And that's just a variation on the sort of plastic story. I've never seen anybody do the microplastics as a health problem, but I have heard people talk about it as a health problem. So when I say that, I've never seen anybody do the valuation part as a health problem. But if you can estimate the epidemiology relationship, that's just your production function. And then you just need to take from the literature some sort of notion. If the plastics are killing people, it's really easy. There's a big Lancet paper 3 or 4 years ago by a whole host of people that look at air pollution problems around the world, and I would just take their mortality and morbidity, numbers, because they had a way of doing that across countries. So, if you wanted to do that, you just lift their sort of health valuation numbers, and then it's just an epidemiology problem. Okay, did that sort of help answer that one? Anyway, this is the way lots of ecosystem services are sort of dealt with. There's sort of a technical relationship which drives things, and then there are monetary values enter in different places. Okay, so I'm going to show you a recent variation of this that's gotten a fair amount of attention. That's of course a paper of mine, so it's easy to talk about. This is a paper with Fang Wen's son, and this is in the proceedings of the National Academy of Sciences in 2020. So the US is frequently hit by tropical cyclones, which in the US are often called hurricanes. There are 88 of these. They hit 236 coastal counties, which are sub-state areas. There's a lot of damage caused by storm surge, wind, and flooding. There are ways to reduce it, hardening infrastructure, building codes, what your disaster response effort is. But it's also the environmental input, like hardening infrastructure and building codes. All of these things basically cost money. The environmental input, which you're just sort of stuck with if you're building the houses, is how many wetlands, what type of wetlands you've got. And so here we're going to look at the marginal value of wetland preservation in preventing property damage. And we, of course, are not the first to do this, although this may be the best of the studies of this sort. There are a number of studies, various places. So some of the early studies on this topic were done involving shrimp farms in Thailand by Ed Barbier, who's at Colorado State University. Okay, we just said that. We just said that again. That's like a completely useless slide. Okay, well, we've got to construct a whole bunch of geospatial variables. The area hit by each tropical cyclone, the wind speed hitting the area, the angle at which the storm hit. And that's because if you're hit on the right side, you push water onshore. And if you're hit on the left side, you blow water away from the coast. We're going to actually have a whole bunch of wetland characteristics where the wetlands quantity is going to vary over time, where the wetlands are located. The type of wetlands, we're going to be able to answer some long-standing questions in the science literature about the effectiveness of different types of wetlands. And then we're going to map the properties at risk at a very sort of fine spatial level, which in the US is known as the census block group level. So you could think of this as sort of 1 kilometer grid squares. Okay, so what does the stimulus data look like? So we're going to treat these storms as what's called exogenous. We may know the overall sort of pattern of these storms, but the storm, from the perspective of a house at any single point in time, the actual storm tracks are random, and so the storms are of varying intensity. Traditionally, the British measured these things in knots, which is an ancient sort of maritime one where they let out a rope and they counted the knots to figure out how fast it was going. But anyway, cyclones are measured in knots. This is 1 year of the wetland coverage. So these tropical cyclones come in and hit the Atlantic and what's called the Gulf Coast. And anyway, green are the saltwater wetlands, and the freshwater wetlands are brown. Those are mapped at a pretty fine scale. Here's an example of one of the bigger hurricanes that hit the US, Hurricane Katrina. And what's interesting here is that we can see it came across and it hit the state of Florida. And when it hit the state of Florida, it was actually a much smaller storm. And it went across the Gulf of Mexico. The water was quite hot, and so it grew in speed. And anyway, it comes up and it almost hits the city of New Orleans, not quite head on. It's going to hit New Orleans on the left. And in addition to mapping all the wetlands and whatever, we need one more thing. For each storm, given the nature of the storm and its speed, we're going to have to estimate what's called the storm surge impact region, which is in the science jargon sometimes called a slush model. So given the speed of this hurricane, all the pink areas were potentially at risk. Here there's going to be a first and a second stage model. And this is not sort of uncommon. So a lot of these storms, particularly the weaker storms, don't do any property damage. So we're going to have a first stage model, which is just, is there property damage or no property damage? And it's going to be a function of wetlands and storm areas and things like that. And then we're going to have a second stage that says conditional on there being damage, how much damage is there? And we're going to do the log of the damage, and it's basically going to be it's going to be the same variables in there. And we're going to control for the fact that we've got this panel data structure, so that we've got states and county and time and whatever fixed effects, so we can control for lots of different things. So the first stage, given how I'm not going to spend a lot of time on, so 65% of the time when a county is hit by a tropical cyclone, no property damage is reported. And the probability of having positive damage is, of course, increasing in wind speed, the storm impact area, and being hit on the storm's right side. So what this means is that most of these counties, when they're getting hit and there's no damage, it's at the low end. The storm impact area is not big, and you're being hit on the left side. It's decreasing in wetland coverage. So, and this is an interesting notion here. One of the big things that wetlands are doing is actually determining whether or not there's any property damage or not. And so if you only look at the second stage, which a lot of people do, you're missing one of the big effects of wetlands. Anyway, is this notion that the wetlands just actually are pretty good at preventing any damage at all. It turns out that the wetlands are not going to be nearly as good at preventing damage from really big storms, and there are physical reasons for that. Okay, there's a large random component. There are tides within any storm track. There can be differences in wind levels. How much rain there is in a hurricane is something that we plan to try to do something on in the future. Okay, the second stage, the conditional damage model, shows wetlands significantly reduce property damage. The wind speed is really big. We come up with the energy in the wind goes up with the cube of wind. We actually come up with the first really good estimates of how the property damage goes up with the wind. Being hit on the right side increases damage by 140% relative to the left side. And the damages are increasing, but at a rate less than 1-to-1 in terms of storm area and the property at risk. And part that's because the more expensive houses are better constructed. So the key relationship here is that if wetland coverage drops by 1%, you reduce the wetland coverage by 1%, the property damage from one of these storms goes up by 0.6%. So that turns out that is a huge sort of effect. Not nearly as big effect as the wind speed. So anyway, a 1% change in the wind means that the damages go up by a factor of 7. Everything's sort of well defined in this thing, and at the conditional level, we're explaining about 50% of it. And anyway, our efforts to put in rainfall and tide says that even more of it's predictable. We show that there's no difference on average between fresh and saltwater things, and this turns out to be due to particular geographic configuration. Most of the houses are up on sort of rivers and streams that are going into the ocean, and that's where the freshwater helps. The saltwater wetlands are right on the coast, and they actually do better things in terms of knocking down the floods. The same thing's actually true between forested and non-forested, again, for very different reasons. The forested wetlands are way better when you start looking at particular storms. They're way better at knocking down the wind, but the non-forested wetlands turn out to be way better at absorbing water. To get the value of the storm protective services, what you need is, anyway, this is the change in the expected damage with the expected wind. And to get the expected wind, we have to have some way, and this is pretty common in, I should say, in studies like this, and it's true of all the climate change studies. So for the climate change studies, you need some source of what's predicting the climate's going to be in the future. Here we need the probability that different places in the future get hit by different levels of wind. And so the government, NOAA funded a big science group that came up with hurricane probabilities. And anyway, we use their estimates. They use we fit them to a gamma distribution and set an upper limit on how big the hurricanes can be. So what falls out of that, these are the annual marginal values of coastal wetlands for property damage predictions. This is $1,000 per square kilometer. And you get very interesting sort of notions. About 6 months after the study came out, there was a giant hurricane that hit right down here. If you can see my cursor on D, and there was it was really big. And so there was some notion that it was going to do a lot of damage because it was a really big hurricane. And, we looked at our model and we said, not going to be much damage. There's a lot of wetlands in front of what's going to get hit. And sure enough, the hurricane dissipates its energy over the wetlands. What you can see though is the really big values are in places that don't get hit nearly as often, but have lots of property at risk. So New York City got hit by Hurricane Sandy. Occasionally Boston gets hit. In a lot of the recent storms, it turns out that Tampa and St. Petersburg, Florida, this is really low and there's lots of property. So anyway, it's a combination of where your wetlands are located. Surprisingly, the values for Miami aren't really big, but that's because Miami's got a huge amount of wetlands, but they're on the wrong side. They're in the Everglades. And so, storms aren't moving that direction. So they're where the wind goes. Okay, so One of the things about estimating models like this, and we'll see exactly the same thing in the travel cost model, the big travel cost model I'm going to show you in a minute, is once you've estimated models like this, you can just keep using them over and over again, and they stay good for quite a while. You keep feeding into them sort of new science inputs, but the economic parameters, which the economic parameters are these things, you know, how the wetlands are changing and the wind's changing and all these things are changing, but the coefficients aren't changing. And so that means these models typically after they're estimated are you know, they're often used for 10 or more years. So this is a hurricane that happened the year after we closed off the data for our project, which was 2016. So anyway, toward the end of 2017, Hurricane Irma, which was a really big hurricane, came, and it came up, and you can see that it's big. This is the state of Florida right here, and you can see this hurricane was sufficiently big that it, you know, it was covering both sides of the state. And anyway, the wind is pretty intense. Turns out that this area right here, you can see the slush model. This isn't going to do a whole lot of harm because this is mostly a giant national park, the Everglades National Park, which is built around wetlands. But as we get up further, it's going to do more damage. And we can calculate that since 1996, Florida lost 2.8% of its wetlands in the 19 coastal counties that this hurricane is going to impact at tropical storm or greater speeds. And what our model says is that the loss of these wetlands increased property damage from this one really big storm by about $400 million. And to put that in perspective, this was a really bad storm. This is one of the worst hurricanes that's hit the US, and it did $40 billion worth of damage. So the loss of these wetlands was about, you know, would have reduced this damage by about 1%. But this isn't a really big loss of wetlands. And the official US government policy was that they shouldn't have lost any of these wetlands. So anyway, all of this is sort of due to sort of bad regulatory efforts that let them lose those wetlands. Okay, questions about how this production function approach works? You know, this is you know, what you can see here is that the wetlands are providing this ecosystem service. The property values are providing, and if we go back up here, the property values here are providing our P. There's another part of the paper that looks at building codes and other things. Anyway, turns out that building codes and wetlands are somewhat substitutes for each other, and the wetlands turn out to be cheaper than strengthening the building codes, which are actually pretty expensive.
I have a question, Professor. The production function approach usually applies to the agricultural or fishery or like that kind of a landscape rather than the human aspect. You mentioned that this can be used for the human, this plastic issue. I mean,
Yeah,
are there any applications on that?
Right. So, I mean, in other words, if we thought about agriculture, the production function approach originally came from agriculture. And, but once you saw how it worked, you know, if you have an epidemiology approach where exposure to air pollution, you know, so if exposure to air pollution causes increased mortality, you know, what you're going to do is you're going to get variation across cities and across time in how much the air pollution levels are varying. And so it turned out that one of the well-known paper in environmental economics dealt with the problem that, you know, people move between cities and whatever, and so air pollution effects are cumulative. And so what they decided to do was look at infant mortality. And so in that case, you know, there's no long-term exposure, and they were able to show that, and this is something that had the epidemiologists had never been able to estimate it. And what they showed here was that there was a very good size effect of changes in air pollution levels on infant mortality by using the fact that these, you know, the expecting mothers were not moving between cities very often. And so, you know, they were just being exposed to different levels of air pollution. And so you could estimate, you know, something that looks almost exactly like this. The dependent variable, instead of being property damage, would have been, you know, infant mortality. And the variable, you know, instead of log of wetland, it would have been, you know, some air pollution exposure variable. And then you would be controlling for, you know, age of the mother, income, you know, lots of those things. And so that's just a production function approach. And, you know, there are lots of these. If you know, the output variable here could be, you know, how much revenue the fishing boats were, you know, the fishing boats in a particular area were getting. And, you know, there could be a bunch of variables describing, you know, how many fishing boats, how many big, you know, all, you know, whether they were selling to restaurants, whether they were selling, you know, to the Japanese market, whatever. And, you know, one of the variables there is just, you know, some type of pollution variable. You know, that's all of those are production function approaches. And so a huge amount of the stuff on ecosystem services, this is the way to plug it in. So with a lot of the other things, you know, it's hard to get the subtle sort of effects of these things. And that's because the nature of a lot of these ecosystem services is they sort of build up. And, you know, it wouldn't be uncommon, you know, there's no reason, you know, particularly when you're looking at different types of pollution or whatever, for there to just be one ecosystem services variable. You could, you know, very well have multiple ecosystem services variables here. And that's, you know, that's effectively what we did here. You know, we swapped out the wetlands here by letting there either, you know, by having different variables for fresh and saltwater variables. So, and this is done with total wetlands and then an interaction term. But anyway, that's how you get these node differences. But then when you look at particular types of storms, you see that this node difference effect is, in some sense, because these things provide better types of protection against different types of storms. And so on average, they sort of cancel out. And that's, again, consistent with there are a bunch of claims in science literature which are contradictory. And, you know, we sort of show why they're contradictory. Okay. Any more questions? So
I have one.
Yes.
Yeah, you showed one slide where, you know, the valuation of square kilometer of mangroves, I think, was $1,000.
Yes. Yeah. Actually, some of these wetlands are mangrove, and
Yes.
and the mangroves here are forested wetlands, and
Yes.
so yeah, there are a bunch of studies. One of the things you see here is, in particular, the mangroves are very good nursery areas for fisheries. And so you know, as you get rid of the mangrove forest, you do, you know, harm to your fish, you know, to your fish spawning.
Yeah, no, the valuation may be okay, but when in terms of a disaster, as the mangroves to be totally destroyed, like in a hurricane or in an oil spill,
Right.
to claim that kind of valuation?
Yeah, so if you thought about, you know, it's not clear who you're going to sue for the hurricane or cyclone, but if it's an oil spill, I mean, in other words, let's say the oil gets into your mangrove forest, and the only thing your mangroves forest here are doing is helping support your fisheries. If you had a model which said, hey, if I get rid of or do a lot of harm to, you know, 3% of my mangrove forest in a particular area, it's going to, you know, have a 6% reduction in my fisheries catch, not this year, but, you know, next year and subsequent years. Right, you know, you can just use that relationship to figure out what the loss was due to the to oiling the mangroves, and you know how many time periods would be, you know, that's what, you know, that's where these sort of simple methods of calculating the damages cause problems, because your oiled wetland, the first year it's going to be pretty bad, but you know, over time the oil is going to break up, and so these services of the forest are going to return, you know, over some time horizon. So you might say in, you know, years 1 and 2 you get rid of all the services, but at some point they sort of, you know, come back more or less quickly. Okay,
Yeah,
so
okay, thank you.
Anyway, lots of papers out there with those sorts of things. So let's think about the travel cost model. The price of a recreation at a site is not only the entrance fee, and lots of times
I have a question.
Yes.
I have a question, sir. Actually, in Sri Lanka, normally we want to measure the ecosystem services in that production function method. But due to the lack of physical and biological parameters, we are unable to do it. And normally we do that benefit cost transfer method. The research done by the same area, and get the literature values, and we use those values with our mangrove cover area and the reduction of mangrove cover area. Is it okay?
So the answer is particularly on the, you know, the physical biological side, you can transfer those production functions. You know, all of the issues in transferring those production functions are the same as actually transferring the monetary estimates, but often easier on the biology side, because, you know, you don't need to worry about, you know, people having different types of income and economies having, you know, different, you know, fractions in different sectors, and, you know, different, you know, transportation maps. I mean, in general, you know, the notion is the typical notion is if you controlled for enough, you know, all the right things, and let's just take agriculture, you know, that you could take an agricultural production function for, you know, producing rice, and you could move, and the International Rice Institute or whatever, there, you know, basically there's a big rice production consortium research group. You know, their notion is that, you know, you can take your rice production function, and if I control for temperature and water and you know, soil quality and application of fertilizer and all those things, that, you know, there's no difference between countries in terms of the rice production function. You know, there's no reason, for instance, if, you know, if you were to just, you know, say you're on, you know, the Indian side of the Indian-Bangladesh border and the Bangladesh side, and, you know, you wouldn't think that, you know, a short distance either direction on the side of the border is going to change, you know, the rice production function. So yeah, so anyway, lifting of the actual biological production functions is like a really common thing to do. I can't say that I'm an expert in doing it because I'm not a biologist, but it's done all the time. Yeah, and an economist, you know, economists are apt to, you know, do that when they, you know, want to compare things across countries and whatever. Okay, travel cost model. So this is built on the notion that at any recreation site, there's a cost to get to the recreation site, even if the actual entrance fee is zero. And that's because there's a monetary and a time cost to travel to it. And what this is going to do is it's going to say visitors who live different distances from the site face different implicit prices, and it's these price differences that are going to allow you to trace out the demand curve in terms of the total number of visits. Person named Harold Hotelling, who did lots of amazing things, started modern finance theory, modern industrial organization theory, multivariate statistics, got asked in the late 1930s, and I'll describe what he said, but that in just a minute on the next slide. But anyway, he conceptualized how to do this. It got operationalized in the 50s and 60s, mostly at Resources for the Future, where I did my original sort of work on contingent valuation. And then Gary Becker, who's a Nobel laureate, showed that there's just a huge set of problems in economics, which he called household production function problems, where households get utility from combining marketed and non-marketed goods. And anyway, this theory covers lots of things, but here what we're going to show is the travel cost analysis and averting behavior, special cases of the same underlying model. So let's think about Hotelling's original insight. Remember that the Park Service is going to come to him and they're going to say, how much is our national park worth? And that's because they had been asked, in this case, by the legislature to justify all these expenditures on national parks. And what Hotelling said is, take your recreation site, draw circles around it, and you know, you can have the circles of different radiuses. It said, observe where the visitors come from. And originally you could have a sign-up sheet at the park, or you know, originally they actually did this with license plate numbers. The license plates on cars said what county and what state they came from. And you calculate the visitation rate. That's the fraction of the population visiting the park for each of these concentric rings. You know, you're subtracting off the smaller rings. So you're just getting that part of the circle. And what you would see is the visitation rate typically falls as the distance from the site increases. And the economic reason for that is the cost of visiting the site increases as the distance increases. So let's just show you a really simple example. So this is the state of Ohio. They have a park called the Headland State Park Beach. So it's a popular beach site. They're going to do these surveys of people who are visiting this park. So, you know, everybody who's visiting it is taking at least one trip. And so they're asking people how many times during the season, you know, are you coming to the park? And there's a price in terms of the price per mile. We'll talk about that in a minute. But this is the implicit cost. So this park has a zero entrance fee. And what you can do is you can see this is like a really nice looking demand curve. As the cost of getting there increases, you know, you're taking fewer and fewer trips. And so, you know, the people who are effectively living right near the site, of course, are taking lots of trips. And so it's almost a perfect statistical fit. And so what's the value of a trip in the simplest possible case? You just set, you know, you estimate this relationship and you set trips to zero. This is sometimes called a choke price. And so what's the value of a trip to this site? $46.94. Okay. And so there are hundreds and hundreds of these studies. So they're, you know, you can go out to a, you know, any recreation site and, you know, just send some students out and, you know, have a really simple questionnaire. You know, the only trick here is probably, you know, you might need to send them at different points in the season and correct for that. But anyway, this is pretty straightforward. And all you need to do now is know how many sort of visitors or total trip. You need to know the number of people and trips and where they live. But you can then blow up this $46.94 to, you know, it's the area under this curve as always. Okay, so in this individual site model, you have to define the site, define the recreational uses and time frame. You know, are you looking at the summer season? For big, say, national parks and whatever, you run into a problem with multi-purpose trips. That turns out to be really complicated to deal with, so I'm not going to talk about that. You have to determine a per kilometer travel cost and a value of time. In lots of countries, for instance, in the US, for like travel, the Internal Revenue Service, the tax people tell us what the per kilometer travel cost rate is. You have to come up with a time cost. There are really sophisticated ways to do this. 90+% of the studies use 1/2 of the wage rate, which is turns out every time you do is about right. You have to determine the population of interest, sampling strategy, specify your demand model. This is just a straightforward linear model, but there's no reason for it to be, you know, there's no reason for it to not have some curvature. You have to design your survey. These surveys tend to be fairly easy, but you may want to identify, particularly, you know, if you think that you've got pollution at a site, you need to start thinking about, you know, the substitute sites. And what you'll find is that people live different distances from the substitute site. So even in the simple model, you can start controlling for things that would allow you to get at pollution. You collect from the respondents, if we ignore the multiple person trip purpose, just where they are. Google Maps will, if you know where people came from and you know where the recreation site, will come back, and there's a nice little function, I think it's in R, or I think there's one in Stata, that will calculate the travel distance by road and the travel time for each trip. You know, if you specify the time of day, you just estimate the statistical demand model, and then you just estimate the consumer surplus value, which in this case is $46. If you have somewhat more complicated, but anyway, these things are pretty simple, and they work pretty well. This is one of the cheaper things that you can do, in part because you can do it with students in other low-cost areas. So, you know, in the US, there's a whole group of people who work for NOAA, and that's all they do is these studies like this sort of, and they rotate across different sites. So one of my graduate students is analyzing, you know, a set of data that they recently collected on different beaches in Southern California. Okay. The difficulty with the single site one is that usually you're really interested in where exactly people are going, and they're getting to choose from different options, and these are called multi-site recreational choice models. And rather than being based on a quantity demanded problem, this is basically a choice amongst alternatives. And the statistical model here is exactly what you saw us fit for the Malaysia discrete choice experiment. So all this is the revealed preference version of a discrete choice experiment. Anyway, the statistical model is used in all sorts of location and transportation problems, so there's nothing unique about environmental applications. Respondents are assumed for any particular choice occasion that they can only go one place. So variations on these models allow them a set of choices over a season that give them the highest level of utility, and the model allows agents to, you know, there are variations when you look at the underlying math on these problems. All you need is the site they chose and a random selection of unchosen sites. So this is a way to estimate models with a tremendously large number of sites. So let me show you South Central Alaskan recreational fish study that I did with Michael Hanneman and Thomas Wege, that's in Marine Resource Economics in 2009. We're going to have multiple waves of trip diaries to Alaskan households with fishing licenses. So there are a little over 1,000 respondents. Alaska is like freezing cold in the winter, and we effectively bribe these folks by entering them into raffles to get free trips to Hawaii where it was warm in exchange for, you know, they had a chance to win these trips when they sent their diaries in. And there's nothing more desirable to somebody living in Alaska than to go to Hawaii in the middle of the winter. So we had a really good response rate. We're going to look at 13 different species of fish, 29 locations. We're going to let people make choices in each of 22 weeks. And that's going to turn out to give us 30 million implicit choices that people are making. So the vast majority of the people in the state live in what's called the South Central region. There's a little part that's actually not connected to the rest of Alaska, but to Canada. We did a separate study there for them, and the rest of the state is like pretty frozen. So the state count. So anyway, Anchorage, which is the big city, is here, and we actually have Prince William Sound down there, which we talked about earlier. And the most popular places to fish for really big king salmon is down here on the Kenai Peninsula. So how does this model work? So you decide to go fishing this week or not, and then you have how many trips to take. There's a paper in the Journal of Applied Economics, which has the count data version of this. You decide whether you're going to go fishing for salmon, freshwater fishing, saltwater fishing, or whether you're not targeting a particular type. We'll assume that we're going to go salmon fishing. You can go king salmon fishing, silver salmon fishing, red salmon, or pink salmon. And then you decide where you're going to go fishing. So we group the different fish. So some of the more popular fish are in their own ones. Then we have, you know, a group of sort of less common freshwater fish and a whole bunch of saltwater fish grouped together. And this is what a canine king, this is what a canine king salmon looks like. So anyway, these things are monstrous. Okay, so site choices are characterized by a whole bunch of attributes, just like you saw in the Malaysian forest example. Here we've got several measures of fishing quality and quantity. We've got what the fish catches were in the previous year in the same week, and we have announcements from various places of how good the fishing quality is. We have crowding levels. One thing is it gets cold in different weeks, and so different places the temperature starts to change. So we got things like temperature. And what this is going to do is it's going to allow us to estimate the economic effects of changing quality. And, and what you can see is that, you know, all you would need to do here is add attributes related to contamination in some fashion. If you had sites that, for instance, had more, you know, you could characterize sites by how much, you know, plastic was out there, or, you know, how much oil was out there, whatever. We can also make sites unavailable in specific weeks because we're talking about salmon. The salmon go out to the ocean and spawn, and then they come back in a fairly narrow time window. So sometimes they're there and sometimes they're not there. And you can measure closures by just whether or not the site's available. And so this framework gives you a really easy way to estimate the recreational fishing losses from closures. And we'll see that in a minute. You get this giant tree structure, which you can't read, but, you know, at one time when we first estimated this model, was actually the world's biggest logit model, and it took several hours on a Cray, which I think at the time was the fourth fastest computer in the world. But anyway, you can now estimate this model on your desktop computer. All it wanted was a huge amount of RAM memory to do that. So anyway, no estimation problem. So what we're going to do here is in week 13, which is a really big week for king salmon coming back to the Kenai River, which is where the woman with the giant, you know, holding the giant king salmon was. We're going to close down the Kenai River, and there are two different sections, parts of the Kenai River, and that's because they use different types of fishing tackle to catch the king salmon on the river. And this is the most important sort of king salmon fishery in the world. So what this says is that originally conditional ongoing fishing for king salmon in this week, 45% of the people who went fishing for king salmon went fishing on the upper stretch of this is actually the upper stretch of the Kenai River. This is the lower stretch of the Kenai River. And so what we're going to do is we're going to close down those sites. We're going to close the Kenai River to fishing, which the Alaska Department of Fish and Game does that for rivers fairly often because they have people counting the different species of salmon that are going up the river to spawn. And if too few salmon are returning, they close the fishery to recreational fishing. So anyway, we're going to do that, you know, just as and once we estimated the model, the state of Alaska Fish and Game uses this to do exactly this. And they used this model for, I don't know, 20 years or so. The interesting thing here is you can see that what's going to happen is that a lot of these people are going to move to Site 19, which is the Anchor River. And, you know, you can see that they start to move it at another place. When the Alaska Fish and Game people see this, they get very concerned because, you know, they say if 40% of these anglers are all going to show up at the Anchor River, they're going to wipe out the king salmon on the Anchor River. So they actually, if they saw this, they're going to close this river at the same time, but we're not going to do that. What's then going to happen, this model has got all sorts of substitution on it. So originally, we're now going to look at people who were fishing for salmon, and originally 24% of them were fishing for king salmon, and then, you know, different quantities for red, silver, and pinks, which are sort of less big. And once we close the king salmon, though, we're going to cut the fraction of people fishing for king-eye kings in less than half. We can keep doing this, and we see that the substitution gets less and less. We see that the overall fishing for salmon, just from closing the Kenai River to king salmon, is going to reduce the amount of salmon fishing by about from 53, you know, 53% of the people doing it to about 50%. And we can also see that we're going to increase the number of people who don't take any fishing trip from 70% to 71%, and we're going to reduce, you know, a number of these. So to count for this whole pattern, if we just looked at the Kenai king salmon, we're not going to get the whole set of effects. So what does this say about what's going to happen? We predict that 692 fishing trips that would have been taken if the Kenai King, if the Kenai River had been opened, are not going to get taken, but almost 46,000 trips are going to get changed. They're going to get reallocated from where they were being would have been taken to someplace else. This is going to tell the Alaska Department of Fish and Game that if they close those sections, the cost to them of protecting the salmon run in terms of lost consumer surplus is $482,000. And then this is hooked up because we know what the fishing trips are. We know the number of fishing trips, and we know where the fishing trips are being taken. This is hooked up to a regional input-output model, and that's going to generate the reduction in expenditures that people are taking. So this is gasoline and you know, fishing bait and tackle and boat rentals and things like that. So anyway, there's going to be their expenditures on fishing are going to drop by $100,000. Okay. Questions about how that works? Again, these are pretty heavily used models, and you know what you can see is that you know, a lot. You know, Great Britain has a giant model of outdoor recreation. They have this huge survey. I don't know, interview maybe 1 million people over the course of a year, and you know, it allows predictions for dozens and dozens of types of recreation. And you know, using that data, we've been able to do things like answer the question, you know, do people who own dogs actually get more outdoor recreation? And we can do that by connecting the British recreation data with weather data, and we showed that when it rains, the people with the dogs keep engaging in outdoor recreation, but the people without dogs are much more likely to stay at home. So if there are no questions, averting behavior is an identical framework, and what you can see here is the impacts of the spill, like advisories to not eat fish, now just become a site attribute. Or if you close the site, then impact site availability. So you can see that, you can, just like we closed the Kenai River, we could have closed it because there was contamination, or we could have changed the quality or quantity sort of measures of fishing, and you would, those just propagate through and then give you, a set of changes. If you change quality, you're going to change the number of fishing trips, you're going to reallocate fishing trips, and you're going to change consumer surplus and expenditure. So it works just the same way. But there are other ways to implement averting behavior models. There are a whole bunch of natural experiments, and all of these accidents look like natural experiments. So nobody was counting on, the express pearl, dumping all this plastic in. And so, what that means is that you don't need to estimate both the demand and supply. You can just look and see, how the spill shifts demand for products. Now that you only have to do one of it side. You can also do hedonic pricing models, and that's going to look at how the spill influences prices for a good or a service. The key thing in any averting behavior model is the person is taking the averting behavior to reduce the harm to them. And what that means is that how informed the consumers are is always the key issue in an averting behavior model. So, one notion is to assume that they're perfectly informed about what the objective levels of contamination are. But that's rarely the case. Some people won't know. Some people will perhaps overestimate the problem. So anyway, all the academic papers, they're focusing on this notion of what the consumer information is the typical thing. So let me give you a series of quick examples here. So in a really early study, the state of Oregon, somebody was putting out a sort of bad pesticide, mercury-based pesticide, which anyway, they sort of quickly got rid of once they figured out what they were doing. And this reduced hunting for game birds. And they were able to estimate a travel cost type model. And so that resulted in $1.3 million in lost consumer surplus due to this recreational bird hunting. And then another paper, which is, there are a whole bunch of these types of papers. So there's a consumption advisory for PCB contamination in recreational fisheries. So the PCBs come from electrical transformers and they get into water. And what happens here is that the government puts out advisories and says, hey, either don't fish or don't eat as many fish from this. And so anyway, Jacobson et al. In 1988 in the American Journal of Agricultural Economics show that these fishery advisors, you should say, reduces fishing and alters trip patterns, resulting in $47 of lost consumer surplus per Tennessee angler. There are a fair number, several million anglers in Tennessee, so this is actually a pretty good sized number. This is a natural experiment paper. So the U.S. Environmental Protection Agency came up with a new requirement that communities had to be noticed in their water bills if they had different low risk contaminants in their drinking water that hadn't been removed. And if people got these notices in the communities that this happened, the bottled water sales increased by 22%. So the drinking the bottled water is an averting behavior response to the low risk contaminant notifications. And so, you know, note here, you're just taking the number of bottle, you're taking the, you know, the quantity of bottled water times the, you know, price of the bottled water. And that's going to be the averting behavior loss. But the key thing here is that, you know, if you read this paper, the likely loss is much larger because most people don't read these notices in their water bills. Every time there are other sort of disasters, the Fukushima nuclear power plant, they send out radiation warnings that, you know, oysters from different regions might have problems. And so anyway, that reduced the price of oysters from the larger Fukushima region relative to other oysters. So anyway, there are just lots of these averting behavior studies that, and that seems really relevant to lots of different contamination. Questions?
I think from today or tomorrow, they are going to release the water or cooling water from the Fukushima.
Yeah.
So there might be more studies and more contamination, though IAEA has approved it.
Right.
Yeah. And also the shellfish poisoning in USA, we read a lot. You have not mentioned about that.
Yeah. So anyway, they're just, you know, there's all sorts of you know, there are all sorts of things, and these things are done, you know, all over the world now, and these turn out to be often, you know, easier, less expensive studies to do. For instance, this study by Josh Graf-Ziffen and cohorts, I'm trying to remember who else, Matt Neidl at Columbia and Wolfram Slinker at Columbia. You know, they just use commercial data from, you know, supermarket sales and just matched it to the communities where they've gotten these low cost notices, these low risk notices versus communities that they hadn't. So, you know, a lot of the oyster prices, you know, all you need basically is, you know, what the prices of oysters are for different regions, and to get a damage number, you need, you know, the number of oysters being sold, because two things might happen. The extreme cases, you're selling the same number of oysters, but getting, you know, a lower price for them, in which case it's the number of oysters times the drop in price. But you could also basically sell fewer oysters, and that makes the loss even bigger. Okay, hedonic pricing. This is again similar to a discrete choice experiment, which is a stated preference version. So there's a good being bought and sold in the marketplace, and it's just a bundle of attributes. So just like in the forest case, there are a whole bunch of attributes. They're hedonic wage ones, where this is how much money people get paid, you know, hourly wages on jobs. And so the higher the risk of, say, being killed on the job, holding other job characteristics constant, those jobs pay more. And one of the ways they get the statistical value of life estimates is to look at those risk premiums. Hedonic property equations. Households are bundles of characteristics, bedrooms, bathrooms, you know, yard sizes and whatever, coupled with locational amenities, air pollution, and crime levels. And in this case, you can say, what's the value of an air quality improvement? Is just the difference in the predicted price of houses that are otherwise statistically equivalent. So a house with the same number of physical characteristics and the same locational amenities, except for the change in air pollution. And so the non-market value there is just the difference in the housing price once you know, between the statistical estimates for those two sort of stylized houses. There's a other similar variant, which is a hedonic product regression. The product's just a bundle of attributes. If you buy, you know, the PC on your desktop has got different amounts of RAM, different processor speeds, you know, different hard drive storage, you know, whatever. And, you know, you can just regress the price of the personal computer on the bundle of characteristics where the brand, like, you know, Apple or Hewlett Packard is also an attribute. And the regression of that price on the attributes reveals how the market is pricing those attributes. So you can see exactly how you could do this if you regress the price of a particular species of fish taken from different locations. You could regress it on some type of objective measure of contamination, and that's going to reveal the economic losses, at least given the objective measure. Reputational impacts can be done by using subjective measures of contamination. And, you know, the subjective measure of contamination here may be as simple as in the, you know, Fukushima example. You know, this is just being done here. The subjective measure, which is giving you the reputational effect, is just, you know, putting an indicator variable in for coming from the Fukushima region. Okay, so anyway, again, these are pretty easy to estimate. They get harder when you start talking about bigger changes, because this is an equilibrium at just one single point. And it turns out the big problem with hedonic pricing is it gives you the equilibrium sort of supply and demand, but it doesn't tell you what happens if you have a big change. And there's some other perverse problems that you can run into. So if we take the hedonic pricing equation for a house and we look at Los Angeles, you get really nice sort of patterns for housing prices in Los Angeles varying with air pollution, because air pollution varies a lot over the greater Los Angeles area, which is huge. But if we looked at Denver, Colorado, it turns out the hedonic property equation doesn't work with regard to air pollution, because there's one giant big brown cloud that hangs over the whole city, and everybody sees the same cloud. And so if you have environmental contamination that's spread over a large enough area, then the hedonic pricing is not going to sort of stop working, because, you know, everybody's being exposed to the contaminant, and so there's no difference. So this approach is going to rely on, you know, having lots of sort of price differences as a function of whatever you're interested in. Okay, just have a few more slides.
Richard?
Yep.
According to our schedule, you have about another 15 minutes. Is it okay with you? You can finish and you'll be okay? Yeah.
Yep.
Okay. Yeah, okay.
That's probably time-wise going to be just about perfect. Okay, let's think about some other sort of not strictly economic approaches, but that insurers tend to like. One is replacement cost, and the little formula that the insurers have, and sort of a good way to think about this is you own a car and you're in a car wreck. What does the the car can't basically be repaired. So what does the insurer want to reimburse you? They want to give you the cost of replacement. So that's buying effectively a new car minus the depreciation between the new car and what your old car was. So if your old car was 3 years old, they want to subtract 3 years of depreciation off of it. And if your car, which can't be repaired, has a residual value, say you could sell it for some amount to somebody who was just going to scrap it and use it for used parts or whatever, they would want to subtract off the residual value. So it's, you know, you can say, okay, and then, you know, that's sort of a good formula. They're going to buy you a new car, but they're going to say, well, the new car is better than the car you had because you're old, you know, you had 3 years to drive your old car. So anyway, that's the depreciation. And if you can sell the, you know, the non-functioning car for something, then they want to subtract off, that's what they're going to pay you. So anyway, depreciation's not an issue if the replacement good is of similar age and condition, and the damaged good has no value. And what you can see here is, you know, if the damaged car had no value and they buy you a replacement car with the same year and sort of same number of kilometers on it, then, you know, this replacement works well. There are lots of things for which this is a pretty good approximation of economic losses. If you've got a, you know, fishing fleet and you get oil on the fishing nets, you know, there's not a huge market probably for used fishing nets and whatever, and fishing nets last for a long time. And so pretty much the insurers are happy to buy new fishing nets. The reason economists aren't really wild about this notion of replacement costs is, in general, if you give people a fixed insurance payment, they're typically going to buy something other than a version of the damaged good. And the bigger problem, though, is that for many environmental goods and services, there's like really no way to replace these things, particularly in a timely way. And what that means, you know, let's say you kill 10,000 birds. You know, in the old days, like, you know, 1969, there's this giant oil spill in Santa Barbara, California. And what they wanted to do was, you know, they wanted to pay for the wildlife that had been died in the oil spill by effectively buying, you know, new birds or whatever from some biological supply catalog. And, you know, of course, there's no way to buy, you know, 10,000 mures from some biological supply catalog. Maybe you could buy, you know, 10. But, you know, what that means is that for a lot of environmental goods, this notion of replacement cost, there's just no way to really replace it. And so the cost is either extremely large and probably infinite. But the insurers will often talk replacement cost. And again, for some common things like the fishing nets and whatever, they seem to work fine. You know, if the engines in the boats got oiled and whatever, and they're willing to sort of, you know, pull the engines out and overhaul the engines and whatever, that's, you know, that's probably fine. Another one that often comes into play is prices in similar markets, and what's going to happen here is that once a market for a particular type of fresh fish is closed, then what they really want to do is use prices in similar but unimpacted markets. And you can see that this is, in some sense, just a form of benefit transfer. And the similar prices is going to work well in two instances. One is that there's a world price for the goods. So, you know, let's say there's a world price for yellowfin tuna, you know, net of transportation costs. And actually, just something that should say, hold on. Say relatively small. Sorry about that. So anyway, in local production, small. So, and what that's saying is basically the world price works because the local production is not having a big influence. Or it's saying that there's no spillover effects between the closed market that you're interested in, the market being used for the price information, and the two markets were similar before the spill. And the second one, they're formal ways to assess, you know, how good the similar prices in similar markets assumption is. But this is, again, one of the things, at least on the price side, that the insurers will want to do. And anyway, correctly, it does work in some cases. Where it doesn't work is if they're local markets and the prices vary a lot and there's spillover between the markets. And in particular, the big problem here is, in a sense, a reputational one. You have contamination in one area, but some people will make the assumption that contamination has spilled over to adjacent areas, even if it hasn't. And so what that's going to do is that will depress the price in the adjacent market, even though there's not actually any contamination there, because people think that there is. And so that will undercompensate the people. Sorry. Okay, there's a technique called habitat equivalency analysis. And this is a pure ecosystem services approach that doesn't take account of human uses. And typically it asks the question whether a particular piece of land is a substitute, the ecosystem services on it, or a substitute for a piece of land that had been harmed. And the way to think about this is that any type of habitat equivalency analysis is going to be sort of one of two types, one of four types defined by this 2x2 typology. One is it on-site, which is saying, hey, if I oiled land in a location, what if I buy, you know, some replacement land that's really close to the area that got oiled, and not only is it, you know, close to it, but it's also right on the ocean. And what one would do is call that on-site in-kind compensation. And everybody thinks that on-site in-kind compensation works pretty well. I can give you sort of an example of off-site in-kind. Occasionally in the US, people will damage coastal wetlands in one state in a location where land values are very high because the coast, there are not very many coastal wetlands left, and they will propose buying coastal wetlands at some distant location where those coastal wetlands are cheap. So that's an off-site in kind. And you know, again, when you usually see that happening, that's a, you know, that's a way of sort of avoiding the cost. You often also see a variation of on-site out of kind. You'll have done damage to, say, birds, and what you'll do is to say, okay, I can't do anything about the birds because it's going to take the birds 20 years to recover, but I could build at the site that was harmed. I could build, you know, more fishing docks and picnic tables and nature trails. And that would be an on-site out of kind. And you see that done reasonably often. Occasionally you see off-site out of kind proposed, and economists always think that anytime that happens, there's sort of, you know, there's some real problem. And, you know, the extreme case here is that you could think, you know, I've done damage to some, you know, marine area which is supporting whales, and what I'm going to do is I'm going to buy, you know, land at a different area that's good for tigers. And anyway, because there's no money metric here, there's no way to sort of make that comparison. And so anyway, that's something to worry. In general, this concept just doesn't work for off-site out of kind. And in general, this sort of in-kind off-site is usually a way to, you know, avoid paying the actual cost of which damage. The interesting case is this sort of out-of-kind on-site one, and sometimes you see a recreational demand model sort of being used to try to get at that in a different way. Okay, so let me just give you some concluding thoughts. The literature on determining these economic values for environmental goods and services is now huge. You can search the literature, use the formal tools of benefit transfer to get a reasonable starting estimates for just a huge range of things, and for lots of things that people in government agencies, and lots of policy evaluations, and lots of smaller, you know, natural resource damage assessments for accidents. This is, you know, just generally, you know, the first thing to do, because you'll get some idea about whether you're dealing with, you know, a small issue or a big issue. And the people who, you know, generally engaging with the polluters on the accidents, as long as the amount of money that they don't have to pay is not that large, oftentimes you can get, you know, reasonably good and quick settlements. And that's one of the things that as a government agency, you should be trying to do. And the key thing there is just to make sure that, you know, if what you're looking at is really big, that you know, you don't settle for, you know, way too little to make the public whole. And so the bigger the things look like, the more that you sort of need to do original studies. And that's particularly the case where high precision is needed. And the highest precision tends to be needed when the damages are large and you're in a litigation context where whoever the polluter is fighting paying. And the necessary expense for doing these studies is largely dependent on how much original data you have to collect. And this data collection effort can both be on the physical biological side. If we were to look at, say, you know, the Exxon, Valdez case, there's a huge amount of effort that's going into modeling, where all this oil is going and how big it is, and all the counts on these deaths of birds and whatever. All of those have to have people who can credibly defend all those estimates. And as an economist, we rely completely on the science folks being able to do this. And it also, again, depends on how much precision you need. One of the things that you see in the US is oftentimes, particularly based on either benefit transfer estimates and sometimes on some preliminary work, the government agency will go to the polluter and says, here's basically what we think the damages are. And if you don't agree with our estimate because you think that it's not been done correctly, or you think the confidence interval is too big or whatever, we're then prepared to actually mount a state-of-the-art effort to quantify these damages, and we know how to do it. And that, again, your ability to do that is going to critically depend on what the legal rules and regulations are. So in the US, for these big natural resource damage cases, even though the government has to come up with the money to do the studies, as long as they do the studies at a high quality level and the studies are deemed relevant for the case, then the polluter actually has to pay for doing the studies. And that's where the notion of having, these emergency funds to do these accidents puts the government in a much better position to say, we're basically prepared to prove all of this. Here's what we think it is. Can we come to a reasonable settlement that will make everybody, better off, rather than stretching out this litigation for years and years. The last point here is that in countries where the government has seriously embraced the notion of polluter pays, which is part of almost all sort of the international framework involving the environment, routine and accidental discharges of oil and other things, going into the environment just falls dramatically. And why is that? As soon as companies know that there's a cost to doing this and that the government is going to come after them and charge them for, illegally discharging, pollution into the environment, then just, a lot of this stuff is just, if you take better care, then, these things don't happen. And you also set up systems to deal with them quicker, and the being able to respond more quickly also is going to greatly sort of diminish the harm that gets done. And the difficulty there is that almost always countries have to experience some really bad event to make the sort of changes in their law, regulations, and enforcement budgets to be able to do this. So I will end there. And happy to answer any more questions.
Professor, I have a question.
Okay.
So in the Sri Lankan context, we have this, we did a calculation for the express pearl, but, our compensation will be restricted by the guidelines of the IOPC, the International Oil Pollution
Right.
guideline. Yeah, so it says that whatever estimates based on the economic models are not accepted.
Right.
So this is the point, like, you know, we are really restricted by that guideline. And I know that the US has their own Oil Pollution Act. So what advice you give us in order to, you know, get away from this?
So let me say here, I mean, just because a country has signed the oil, you know, these conventions does not mean that it cannot adopt its own, you know, procedures for damages. And let's take a really simple case that I talked about earlier. You know, a lot of countries just have a per barrel of oil spilled penalty. Okay, and that is completely and totally independent of, you know, this oil pollution convention. So if you have to remember what the oil pollution convention is really, it's what it was set up to do is to say, okay, there are a lot of instances where, you know, one ship runs into something or another ship or whatever, and it's going to spill oil. And this was designed to basically quickly reimburse really obvious spill damages, like, you know, oiling the fishing nets, getting oil in the motors, closing the hotels for a week. Okay, and it does a pretty good job of that. You know, often what the government needs to do, particularly because, you know, a lot of the fishers are small and a lot of the people in the tourism industry are just small businesses. You know, the government needs to figure out how to organize those claims and help put them together. But those conventions are good for that. They intentionally effectively say, we don't believe that they're large scale persistent ecosystem service problems. Okay. And, you know, nothing keeps a country from doing exactly what the US did. And that's to, you know, the US passed the Oil Pollution Act of 1990. And, you know, it fundamentally sort of changed things. And so when they did it originally, all the shippers and all the people doing, you know, shipping oil in big tankers and smaller tankers and whatever said, oh, if you do this, none of these, you know, nobody is going to, you know, sail big ships into the United States waters. And what they effectively did was make the, you know, these ships post $1 billion in liability coverage with their insurer. And, you know, for all the sort of, you know, nobody's going to sail in US waters, you know, nothing changed. They just all basically bought the insurance. And once the insurers were looking at way bigger coverage, it's actually the insurers that clean up, you know, the bad practices of lots of these ships. So, and you can look, you know, there are lots of countries now that have adopted, you know, changes, because every time, you know, one of these big things happen, there's a public uproar which says, you know, why are we in a position, you know, to have this, you know, massive environmental disaster and then have a framework where we can't, you know, recover from it. But, you know, that's why I said earlier, you know, at least in the short run, you're in some sense stuck with the existing laws, but when I said, you can actually plot out various planning exercises, and in thinking about those planning exercises for different types of accidents, one of the key things in those planning exercises is to look and see how, laws and regulations and international conventions that, Sri Lanka is party to is going to limit the ability to actually make the public whole. So, is here, as I said, this happened. A good way to look at this is that this Santa Barbara oil spill, which was this huge oil spill off the coast of Santa Barbara, which is a city in California, which was one of the events that started the environmental movement in the US. It was such a big event. The government ended up collecting, I think it was like $12 million in damages. And that was 1969. So you could look 20 years later to the Exxon Valdez, which at some levels are a similar sort of type spill. And instead of collecting, $12 million, the government is going to collect $2.8 billion. And, the difference in that was basically the change in the US laws and regulatory schemes for doing that.
One more thing about the discount rate. So in your yesterday's lecture, you talked about when you look at the future impacts, there's a big role in the discount rates.
Right.
So is there any kind of a particular value that country should adopt in doing this kind of future valuation?
I am going to guess that the government, I don't know any governments that some government agency, typically the Treasury Department in most countries, dictate the discount rate.
Okay, but in this country, I have been asking them, they are not, they don't have any clue on that. And I saw this green book in UK that they have proposed something like 3.5 discount rate.
Yeah. So, usually people think of these discount rates as, not including inflation. So there's what you would think of as the real discount rate versus, there's always sort of inflation on top of that. But I might be in the absence of Sri Lanka having one, I might use the British one. I mean, they're at some level they're pretty well respected for their numbers on this, but the US numbers, I think, are these numbers come out periodically. I think it's like Office of Management and Budget Circular 49, which gets updated periodically. And I think the current US rates are 3% and 5%.
Thank you very much. Thank you.
So anyway, certainly the US and the UK have well-established numbers, and I want to say probably the EU does, but almost every country who there are just lots of things that they have to use this number for, and the reason that it typically comes out of somebody like the Treasury Department is that they want to force all the government agencies to use the same number. And, you know, that's because what they're looking at, in part, the discount rate often reflects what they think their borrowing costs are in the world market. Okay.
Yeah, okay, thank you very much. And I just have one more request, whether we could get some assistance from you in designing some of our, you know, CVM surveys with regard to express pearl.
Yeah, potentially I could help do that.
Yeah, thank you very much.
Okay, Richard. Thank you very much, and
Okay.
everyone, thank you for participating. We have already sent you a token of appreciation in advance.
Okay, and
Did you get it from Uwe or?
yeah, so I will anyway, I will try to figure out how to get the video the 2 days from you, as well as the slide deck.
Yes, please.
Okay.
I think Leni and Uwe are going to getting it all together and they will be sharing with us.
Yep.
And you can contact them and
Right,
see
yes.
how we can.
Yeah, I think they're planning to post everything in some common place. So anyway,
Yeah.
I will make sure I get my stuff to them.
Okay.
Okay.
Okay, Richard. Thank you very much. It
You're
was
welcome.
very illuminating, very, I mean, you had a wealth of information, and I'm sure everybody gained a lot from this 2 days of your training. Thank you very much.
Thank
Yeah.
you. Bye.
Bye.
Thank you very much.
Okay.
Thank you very much.
Thank you.
ප්‍රශ්න අහුවකට හරියට උත්තර දුන්නා හරි. ආසාවෙන්. Somebody there, Prashant, somebody did.